Siberia is one of the most remote and mysterious regions on Earth. A land of frozen ground, deep lakes and silent forests that stretch beyond the horizon. Beneath its surface lie stories of fire, ice and time, ancient impacts, vanished animals, strange lights, and unexplained changes in the land itself. This journey explores real places and real events, all part of a vast wilderness that still hides more questions than answers. Batagaika mega-slump, Yakutia. In the far reaches of Yakutia, hidden deep within the Siberian wilderness, the ground has opened into a massive scar. Locals call it the Batagaika crater, but it isn't a crater in the usual sense. It wasn't made by an explosion or an impact. It is a wound in the permafrost, a giant mega-slump that keeps growing every year, swallowing the forest around it. The story of Batagaika began quietly in the 1960s. A patch of forest near the settlement of Popigai was cleared to build roads and facilities. Without the shade of the trees, the sun began to warm the frozen soil beneath. Slowly, the permafrost started to thaw. What began as a small depression turned into a deep gash, and then, over decades, into one of the largest permafrost features on the planet. Today it stretches for almost a kilometre, and its depth approaches 100 metres in some places. From the air it looks like the Earth itself has collapsed inward, revealing an ancient layer beneath the modern world. Each summer, as temperatures rise, the edges of Batagaika retreat. Meltwater seeps into cracks, softens the frozen soil, and entire sections collapse. In some years, the rim moves backward by more than 10 metres. Landslides thunder down its slopes, carrying chunks of frozen ground into the depths. The exposed walls glisten with bands of ice, sand, and peat, each one a frozen record of thousands of years. Scientists who work here call it a time machine. Every layer holds information about past climates, vegetation, and even animals that lived long before humans ever settled Siberia. The lower sediments have been dated to hundreds of thousands of years ago, possibly more than 600,000, making them among the oldest permafrost deposits known on Earth. When these layers thaw, they sometimes reveal remnants of ancient forests, branches still intact, tree trunks preserved in ice. In other spots, bones of long-extinct mammals emerge. Horses, bison, muskox, and other Ice Age creatures that once roamed a much colder but stable land. For geologists and climate scientists, Batagaika offers a rare opportunity. Nowhere else can they walk through a cross-section of Earth's frozen history like this. They collect soil samples, extract pollen grains, and study the carbon trapped inside. Many come here to measure what happens when permafrost melts. The numbers are sobering. As the frozen soil thaws, microbes awaken and begin breaking down ancient organic matter. In doing so, they release carbon dioxide and methane, two of the most powerful greenhouse gases. The more the ground warms, the faster this process becomes. It's a feedback loop. Thawing releases gases that trap more heat, which causes more thawing, but not everything can be explained easily. Despite years of observation, scientists still can't predict exactly how quickly the slump will grow or when it might stabilise. Some parts of the crater expand faster than others. Some slopes stay intact for years, then suddenly collapse after a heavy rain or a warm summer. Beneath the surface, hidden channels of meltwater carve through the frozen ground, accelerating erosion in unpredictable ways. Even the depth of the active thaw zone is uncertain, shifting with seasons and rainfall. When you stand at the edge of Batagaika, it feels alive. The air is cooler near the rim, filled with the smell of wet soil and ancient decay. Water drips constantly from melting ice. Every few minutes there's a faint cracking sound, a warning that another piece of the wall is about to fall. For those who live nearby, the crater carries an uneasy reputation. Some residents of Yakutia call it the gateway to the underworld. They say the ground seems to breathe, that strange sounds echo from within it. To them, it's a place where the earth reveals what should have remained hidden. Researchers who descend into the slump describe it differently. To them, it's a living laboratory, a place where they can see the consequences of a warming planet in real time. They photograph the layers, take measurements, and set up sensors to track temperature and movement. In recent years, drones have mapped the entire area, revealing how rapidly the crater has expanded. From above, it's clear that the mega-slump is pushing deeper into untouched forest. The trees near the rim tilt and fall as the ground beneath them gives way. What used to be a narrow scar has become a massive amphitheatre of thawing earth. Among the most fascinating discoveries are the well-preserved ice wedges exposed in the walls. These are vertical sheets of pure ice formed thousands of years ago when cracks filled with meltwater and froze again each winter. By studying them, scientists can reconstruct ancient temperatures and precipitation patterns. Some of the ice wedges in Batagaika date back to the last glacial period, offering a window into a climate vastly different from today's. Yet, as valuable as this knowledge is, it comes with a cost. The very process that allows scientists to study these frozen records is the same process that destroys them. Each season, new material collapses and melts away, carrying with it information that will never be recovered. What the researchers manage to collect each summer is just a fraction of what is lost to time and warmth. The Batagaika mega-slump has become a symbol of change, not just geological, but planetary. It is one of the clearest examples of how human activity, even something as simple as clearing a patch of forest, can trigger a chain of events that unfolds for generations. It reminds us that the frozen ground beneath our feet isn't permanent. Once disturbed, it doesn't easily return to balance. Some experts believe that more features like Batagaika will appear across the Arctic as the planet warms. Satellite images already show smaller slumps forming in nearby valleys. The landscape itself seems to be awakening from an ancient sleep, reshaping under the heat of a changing climate. Batagaika continues to grow, revealing new layers every year. It is both an archive and a warning, a deep wound in the Siberian wilderness where past and future meet in the melting ground. Patom crater, Kolpakov Cone, Irkutsk Oblast. A cold wind blows over the slopes of the Patom Highlands as our narrator takes us upward, through the dense Siberian taiga, toward a geological oddity that stands alone in these forests. There, rising from the ground like a silent sentinel, is the so-called Patom crater, also known as the Kolpakov Cone, a dome of shattered rock baffling scientists for more than 70 years. The cone was first described in 1949 by geologist Vitim Kolpakov, though even before then, local hunters and villagers knew of the strange mound. It sits hundreds of kilometers from any major settlement, on a rugged slope in Irkutsk Oblast. Its base spans around 150 to 160 meters, its height reaches some 40 meters, and at the top lies a ring-like crown surrounding a central mound. Its weight is estimated at over 1 million tons. From the start, its shape provoked theories: a raised dome with a crater-like depression, but nothing like a crater born of impact. No shock waves, no melted glass, no typical signs of a meteor strike. Yet in that early age of discovery, some held on to a meteorite hypothesis. Kolpakov himself entertained that notion. Others suggested an extinct volcano or a steam explosion. Over decades, each theory has been probed, adjusted, and challenged. To reconstruct what might have happened, scientists have carried out geological surveys, chemical assays, structural mapping, and dendrochronology. In the 2006 expedition, rock samples were collected from across the cone and beyond. These samples reveal mostly limestone blocks, breccia of shattered carbonate rock, mixed occasionally with sandstone or schist fragments. They show no traces of extraterrestrial material or high concentrations of rare elements that would betray a meteor. Mapping reveals a zoned structure: an outer slope, a ring swell, a trench ring, and a central mound. Each zone appears to have formed in stages, not in a single catastrophic impact, but through successive shifts and intrusions. The ring swell, for example, divides into inner and outer parts, hinting that its uplift was not uniform but evolved over time. Chemical and isotopic studies deepen the mystery. Some rock blocks show signs of interaction with fluids heated above 100 degrees Celsius, changing their oxygen isotope ratios. Other fragments are enriched in calcium and strontium, especially compared with surrounding unaffected rock. These anomalies suggest deep fluids injected upward into the cone, altering rock zones along the way. Dendrochronology adds a temporal frame. Trees growing on the cone's slopes have been analysed for growth rings. Some of these trees record stress or disturbance beginning around the 18th century. The formation of the mound is thus estimated to have occurred some 300 to 500 years ago, relatively recent for a geological structure. These observations argue against a meteorite origin. A meteor, or fragments thereof, should leave certain telltale elements or shock features in rock. None were found. Similarly, a classic volcano would leave lava ash or pyroclastic deposits. In Patom, no volcanic rock is present, and the cone is made entirely of broken, reworked local rock rather than exotic lava. Thus, one of the leading models is that the cone was born from within the Earth, an endogenous formation. Deep-seated fluids, possibly rich in gases such as carbon dioxide or hydrogen, might have forced their way upward through cracks and faults. Under pressure, these fluids could have triggered steam explosions, pushing rock upward and creating the dome structure. In effect, the cone would be built from shattered local rock rather than material brought in from outside. Yet even this model has open questions. What was the heat source that drove fluid pressurization so recently? Was there magma at depth or simply thermally heated water responding to tectonic stresses? How many explosive pulses were involved? Did the cone build gradually or in bursts? Then there is the spatial issue. Why here, on this slope in this remote part of the highlands? The local geology includes Proterozoic formations of limestone, schist, and crystalline rock, so there was host rock to fracture. But the cone is effectively isolated. Its shape, the absence of similar cones nearby, means the local conditions must have been unique. Another challenge is rate and timing. Did the formation require centuries of build-up, or was much of it sudden? Some evidence points to multiple pulses, early, intermediate, late phases, each leaving its imprint in zone boundaries. But the precise timings and transitions remain uncertain. Alternate theories persist. Some still consider a meteor hypothesis, ranging from a buried impactor or an ultra-dense iron fragment. Others propose a gas eruption model in which methane or carbon content built up and violently released in a cryptovolcanic event. But these face the same problems: inadequate chemical evidence and incompatible shapes. Even fringe ideas linger. Some observers note tree growth anomalies around the cone, trees that seem to have grown faster or in odd patterns for decades, and suggest unexplored influences. Some propose radiological or hidden human activity, but no credible proof exists. In the quiet of the Siberian forest, the Patom crater endures. It stands as a testament to Earth's ability to sculpt strange forms by forces we only partly understand. As scientists continue to examine its structure, probe its inner zones, and refine geochemical models, the debate between competing hypotheses remains alive. Each new rock sample, each new isotope reading, may push us closer to understanding how this million-ton mound rose from the ground where nothing like it should exist. Lake Baikal's giant ice rings seen from space. A pale dawn stretches over Lake Baikal. From space, the lake lies like a cold blue eye in the Siberian wilderness. Yet in spring, something strange happens. Giant dark circles appear in the ice, perfect rings that span kilometers. Seen from satellites or the International Space Station, they catch the eye and stir the scientists' curiosity. These rings first drew attention in the early 2000s, though astronauts in 2009 helped popularize them. Over decades of satellite imagery, researchers have catalogued dozens, some sources say more than 40 to 50, appearing in different years in different sectors of the lake. The rings are invisible from shore, their scale is only clear from a high vantage. What makes them odd is their structure. The ice inside the ring often appears lighter or more opaque, outside thicker and bright. Around the ring's edge, the ice is thinner and darker, almost translucent. In some cases, the contrast is stark. The diameter of these rings is often between 5 and 7 kilometers, though sizes vary. Some last only a few days, others persist for weeks or even months. Satellite analysts track their timing. Many rings show up in March or April, late winter. Some appear when ice is still thick, others in a phase when melt and refreeze cycles alternate. Their locations shift. The same spot does not always host a ring. Repeated ring formation in specific zones, though, signals that the lake's shape and depth may influence where they occur. Field teams have braved the ice to probe beneath. In selected ring zones, scientists drilled holes through the ice and lowered temperature and salinity sensors deep into the water column, down 200 meters or more. They found that underneath, there is often a warm, swirling eddy of water turning clockwise beneath the ice. This eddy is lens-shaped, weak flow near its center, stronger flow at its boundary. Water inside the eddy is typically 1 or 2 degrees Celsius warmer than surrounding water. The center may remain relatively calm so the ice above it doesn't melt significantly. But along the boundary, currents stir warmer water against the ice underside, causing melting there. That melting creates a ring of thinner, darker ice. Meanwhile, ice outside the eddy remains thicker. This mechanism explains the contrast. Strong heat exchange at the ring edge, weak exchange in the centre, and minimal change further out. The eddies behave like invisible inventors, drawing the ring from below. Scientists have called them lens-like intrathermocline eddies. But what creates those eddies in the first place? The leading idea is that wind, river inflows, and lake shape drive water currents before ice fully covers the surface. When water continues to flow and swirl beneath forming ice, the conditions may align to trap an eddy in a basin or canyon under the ice cover. Bathymetry, the lake bottom shape, and coastline contours help funnel and trap motion. In some zones, underwater canyons seem to pin eddies. Another older hypothesis was that methane gas rising from the lake bottom from hydrate deposits could disturb the water and cause melting patterns, thereby forming rings. But field measurements and modelling weaken that idea. Many rings occur over shallow zones where no known methane vents exist. Methane-driven upwelling alone fails to account for the scale and placement of many rings. In 2020, a ring formed in the southern Baikal near Kultuk Bay, a site under intensive study. Multi-satellite data from Landsat, Sentinel, MODIS, and radar altimetry documented ice colour changes in unprecedented detail. The ring emerged over days, darkened, then evolved with shifting reflectance patterns. Analysis showed how water infiltration into ice, air temperature swings, and eddy dynamics combined. In that case, the eddy seems to have existed before ring formation. Only later did the visible ice pattern appear, as melt and refreeze layered over the structure. Tracking how ice flows moved exposed how the eddy exerted rotational force. A flow inside the eddy rotated clockwise. One on the boundary sped along. The speeds matched expectations from eddy models. In that sense, the ice ring becomes a surface signature of the hidden vortex below. Still, uncertainties linger. Why does an eddy manifest as a ring only some winters and not others? Why do eddies sometimes form without a ring above? What thresholds of temperature, current strength, and ice thickness are needed to unveil them? Also, how deep do these eddies extend and how stable are they over time? In some years, strong winds, warm air, or snow patterns may disturb the ice before the eddy effect solidifies. Meltwater infiltration or snow cover changes the ice's optical properties, hiding subsurface structure. Meanwhile, the timing of ring appearance suggests that the window for ring formation is narrow, a fragile balance. Because of this, many ice rings fade before they can fully develop or are swallowed by breaking ice. In other years, they may freeze over or melt too quickly to record. That makes them elusive, rare, and compelling, glimpses of a dance between water, ice, temperature, and motion. When the satellite passes overhead and a ring appears, it is a signal, a marker that under the frozen surface, currents swirl, heat pulses, and hidden eddies exert force on the ice above. In Lake Baikal, those rings are not art, legend, or myth, but natural signatures of fluid dynamics in one of Earth's largest deep lakes. Vitim, bolide, 2002 Bodaibo district. A distant village lies quiet in the Siberian taiga. It is late evening on September 24, 2002, when suddenly a bright streak of light rips across the sky. The night is broken by a flash, a crack of thunder, and a wave of sound and shock that rumbles through forests and settlements. This is the story of the Vitim bolide. Witnesses in the Bodaibo region speak of a fireball brighter than the full moon. Some say the whole sky lit up for a moment. Then came a loud explosion, like artillery from the heavens. Windows rattled, dogs howled, and in villages dozens of kilometers away, people were jolted awake. The shockwave pressed over the land. Some felt the earth shaking. The event drew immediate attention. Recording stations, satellites, seismic sensors all detected something extraordinary. In the hours that followed, researchers began to assemble the timeline. At roughly 1649 UTC on September 24th, which was about 22 o'clock local time, satellite sensors designed for monitoring missiles picked up a bright flash over the Vitim River basin in Irkutsk Oblast. Infrasound arrays, some over 4,000 kilometers away, recorded acoustic signatures timed to that same moment. On microbarographs, a strong infrasonic wave arrived from Siberia. Back on the ground, locals reported hearing multiple booms, as if bombs fell. Some say they saw fragments or glowing debris falling in forested areas, but recovery on the ground was minimal. Dense taiga, rugged terrain, and swampy land made searches difficult. No large crater was ever confirmed in association with the event. Scientists turned to the data. The infrasonic signals suggest that the bolide exploded in the atmosphere, not striking the ground intact. Energy estimates vary, but many place the yield between 0.2 and 2 kilotons of TNT equivalent. Others, especially some Russian analysts, suggested higher values of perhaps 4 to 5 kilotons. But the range remains broad. The discrepancy reflects uncertainties in altitude, fragmentation, and measurement calibrations. Atmospheric modelling indicates the explosion likely occurred at an altitude of several kilometres above the surface. In such airbursts, a meteoroid disintegrates under pressure as it moves faster than sound, releasing enormous kinetic energy into a blast wave. Fragments may survive, but the majority vaporize or pulverize, leaving only microspherules or dust to settle. Indeed, field expeditions after the event collected small, metallic spherules and microscopic particles in snow, soil, and peat bog layers. These tiny beads, formed under extreme heat, match the chemistry expected of meteoritic material, but they are tiny, dispersed, and found in trace amounts. No massive fragments were secured. Rock and soil sampling in locations thought to lie along a possible strewn field revealed anomalies, microspherules with elevated nickel and iron content. But their distributions are patchy. Some areas produce dozens, others none. That patchiness underscores the chaotic disintegration of the bolide mid-air. A major challenge is reconstructing the meteoroid's pre-entry properties. Was it rocky, metallic, or icy? Speed, angle, composition all influence how it breaks apart. In the case of Vitim, modelling leans toward a stony or mixed rock body, though some earlier accounts considered a cometary nucleus. The lack of a strong meteorite signature and the low yield make confident classification difficult. Another difficulty lies in trajectory. From satellite and infrasound data, researchers approximate a flight path over the taiga, moving roughly from west to east or southwest to northeast. But ground observations are scarce. Tree damage surveys, if carried out, were limited. Faunal surveys in the forest did not find reliable strewn lines of fragments. Seismic stations registered low-magnitude tremors that correlate to the time of the explosion, confirming that part of the energy reached the surface. But those seismic signals are weak compared to major impacts. They say more about the coupling between air pressure waves and the land than about a physical crater. The many uncertainties leave open questions. How large was the original body? Did some fragments reach the ground, buried deep or lost? What altitude exactly did the disruption occur? Did shock waves alone cause damage to forest and soil, or was there localized blasting? In some accounts, local forest plots showed fallen trees or blast patterns, but no systematic survey confirmed a clear butterfly treefall pattern as seen in larger events. The rugged terrain, dense forest, and lack of immediate reconnaissance limited such damage mapping. Still, Vitim stands among the rarer modern examples of a Siberian bolide event. Its flash registered across continents, its infrasound echoed thousands of kilometers. Its aftermath left more questions than answers. As scientists collect more spherules, refine atmospheric models, and search remote zones for fragments, the airburst remains a mysterious event in the Siberian night sky. Yamal-Gydan exploding permafrost craters since 2014. A cold wind sweeps across the flat tundra. The land seems endless, pale and still. Yet in this frozen frontier, huge holes have begun appearing, like wounds in the ground that burst open without warning. On the Yamal and Gydan peninsulas since 2014, explorers and scientists have documented exploding permafrost craters, deep vertical shafts created by violent gas blowouts. Remote sensing first revealed one of these craters on Yamal in 2014. The hole was vast, dozens of meters across, plunging tens of meters deep. Over the following years, more craters appeared in Yamal and across Gydan. Many form in remote tundra, amid shrubs, lakes, marshes. Some are inland, others touch rivers or lake beds. In the field, expedition teams found rims of broken soil, blocks of ground ice tossed outward, and bottom floors sometimes filled with water. Scientists have trekked to these craters with drones, ground-penetrating radar, core drills, gas monitors, and echo sounders. They discovered that each crater is not random. Underneath the tundra lies a complex layering. permafrost above, saturated soil, cryopegs, salt-rich unfrozen water lenses, and below that methane hydrates and trapped gas reservoirs. As summers warm, thaw penetrates deeper, water moves downward, and pressures shift. One new study proposes that osmosis drives much of the action. Meltwater above seeps downward into cryopegs with high salinity. This movement draws more water, raising pressure in the cryopeg zone. That pressure can eventually fracture the overlying permafrost. Once cracks open, methane hydrates destabilize and gas escapes explosively, ejecting soil, ice, and debris. In one documented crater called C17 discovered in 2020, researchers used drone surveys and 3D models to reconstruct how the event unfolded. A mound had built up over years, a heaving mound caused by pressure beneath the surface. Then, between May and June, the surface ruptured. Blocks of frozen soil and ground ice flew outward, some up to hundreds of meters. A cavity opened beneath. In the Sayaka crater, C11, formed in 2017, scientists found that a cavity extended tens of meters below ground ice. Using echo sounders, they mapped steep walls, landslide scars, and active gas seeps. Gas bubbles rise in the crater's water, streaming upward through the water column and into the air. Over the years, the crater's area expanded. Gas seep zones grew. Gas sampling in bottom sediments and water reveals methane of mixed origin, some from microbial decay, some from deeper thermogenic sources, possibly from hydrates undergoing dissociation. In Sayaka, the depth to some seep vents was measured at more than 50 meters below the water's surface. Archive and geological records help frame the context. Scientists have reviewed old maps, permafrost boreholes, and historical studies of tundra gas release. Earlier reports now suggest that smaller gas outflows, seeps, pockmarks, bubbling ponds, were recorded decades ago but never with explosive formation of craters this size. In drilling operations on Yamal, engineers historically triggered gas blowouts, sometimes creating craters or boiling pots, when drilling into gas-rich permafrost zones. These events were recorded during well construction, and they hinted that the region's permafrost layers harbour pockets of high gas saturation. Comparing new crater sites with archived records of soil types, salt content, depth of permafrost, and gas content helps identify which zones are vulnerable. The new 2024 study argues that only in very specific geological settings, regions with cryopegs, adequate salt gradients, a topping layer of thawable soil, and access to hydrates, can these explosive craters form. In the AGU published research, the authors stressed that warming alone is not enough. The right architecture beneath the surface must exist. They argue that the craters result from an interplay of warming osmotic water migration and buried gas reservoirs in just the right configuration. Field teams revisit craters year after year, tracking how their walls erode, how gas emission zones shift, how the rims collapse inward, and how lakes sometimes form in their basins. Some craters fill with water and gradually age into thermokarst lakes. Others remain active with fresh gas bursts. By combining satellite archives, historical drilling logs, field cores, gas assays, and geophysical surveys, scientists are building case files for each crater, when and how it formed, how fast it evolves, and what internal structure enables it. Yet many craters remain only mapped from space. Their depths, internal cavities, and gas distributions await ground missions. As new craters appear and old ones transform, the archives and new data together paint a picture of a landscape shifting under the pressure of thaw and hidden gas energy. Tunguska, 1908, Central Siberia. The early morning sky over central Siberia was calm. The date was June 30th, 1908. The air hung still above the vast taiga near the Podkamanaya Tunguska River. In scattered trading posts and hunting camps, people were waking up to another quiet summer day. Then, without warning, a light appeared in the northern sky, a glowing sphere brighter than the sun. Eyewitnesses later described it as a pillar of fire cutting across the heavens. It left a trail that burned white, then blue, then red. A moment later, a deafening explosion ripped through the wilderness. The shockwave flattened trees for miles. Windows shattered hundreds of kilometers away. Herds of reindeer were thrown to the ground. The blast wave circled the earth twice, recorded by barometers as far as London and Washington. Those who survived near the epicenter spoke of a heat so intense that their clothes nearly caught fire. Others described a roaring sound like iron plates grinding together. One man was blown from his chair in his hut. Another said the sky split in two. People thought the world was ending. But when the noise faded, there was no crater, no impact site, only silence and a flattened forest stretching farther than the eye could see. For almost 20 years, the Tunguska site remained unvisited by scientists. It was too remote, too wild. Only in 1927 did a Russian expedition, led by Leonid Kulik, finally reach the area. They found devastation on a scale that defied explanation. Trees lay in radial lines, all pointing away from a central zone. Over 2,000 square kilometres of taiga had been levelled. Millions of trees had fallen, but many near the centre still stood upright, stripped of branches and bark like poles scorched by invisible fire. Kulik expected to find a crater, maybe a buried meteorite. He found nothing. No hole, no fragments larger than a pebble. The ground was boggy, scarred by small ponds, but there was no single mark of impact. What he did find, however, was an enormous butterfly pattern in the fallen trees, symmetrical, stretching to the northwest and southeast. That pattern became one of the defining clues. It hinted that the explosion happened in the air, not on the ground. Kulik's team collected witness accounts from Evenki hunters and settlers. Many told of the bright fireball crossing the sky from southeast to northwest before bursting high above the horizon. The estimated blast altitude, based on later modelling, was around 5 to 10 kilometres. Using those early maps, scientists calculated that the energy released was roughly 10 to 15 megatons of TNT, around 1,000 times more powerful than the atomic bomb dropped on Hiroshima. Yet all that force had come from an object only tens of metres wide. The leading explanation soon emerged: a stony or icy meteoroid entering the atmosphere at high speed, disintegrating before reaching the ground. As it tore through the air, pressure and heat built up until it exploded in a massive airburst. The blast wave struck the forest like a hammer, flattening everything outward from the centre. Still, details never quite aligned perfectly. Some models suggest the object entered at a shallow angle. Others propose a steeper trajectory. The difference changes the expected pattern of treefall, the spread of thermal radiation, and the position of the epicenter. Some researchers later suggested that the Tunguska body might have been a fragment of a comet, rich in volatile ice. This would explain why no debris was found. It would have vaporized completely. But the thermal effects on trees and soil seem too strong for a pure ice composition. Others favour a stony asteroid, perhaps 50 to 60 metres across, made of silicate rock. That too fits the data, but it leaves questions about the exact height and fragmentation sequence. In the late 20th century, expeditions continued to revisit Tunguska. They mapped tree rings showing sudden growth spurts after 1908, possibly caused by nitrogen compounds falling from the blast. Soil analyses revealed traces of microscopic silicate and metallic spheres, consistent with vaporized rock condensing in the air. Isotopic ratios in some samples slightly differ from local geology, hinting at extraterrestrial origin. Seismic and magnetic records from the era add further intrigue. Instruments thousands of kilometres away registered disturbances that lasted for days. Even atmospheric pressure gauges in Europe picked up oscillations from the event. Nights across the continent glowed unusually bright for weeks, as if the sky held a faint silver haze. Observers from London to Stockholm wrote of reading newspapers outdoors at midnight. That strange luminous night effect came from fine dust particles high in the stratosphere, remnants of the Tunguska explosion reflecting sunlight long after sunset. In the 1990s and 2000s, researchers used computer simulations to recreate the event. Models suggest a 60-metre body entering at roughly 27 kilometres per second, releasing energy between 10 and 20 megatons. The airburst occurred around 8 kilometres above ground, explaining the absence of a crater. The pressure wave would have levelled trees across the butterfly zone, while intense thermal radiation scorched trunks and ignited surface fires. Satellite imagery later confirmed the geometry of the pattern and how it fits with atmospheric models. Drone surveys in recent years have remapped parts of the forest, revealing subtle details still visible more than a century later. The landscape has partly regenerated, but the scar remains, an echo frozen in the pattern of the trees. The mystery, however, has never been entirely closed. A few scientists argue that Tunguska might have involved a double event, a main explosion and a secondary burst. Others suspect that the object could have been a fragment of a larger parent body, perhaps related to Comet Enki, which crosses Earth's orbit. Forensic reconstructions continue. Each new model tries to match the eyewitness timeline, seismic signals, and the observed distribution of treefall. Each one gets closer, but none yet fits perfectly. Tunguska remains both the largest known modern impact event on Earth, and one of the most puzzling. Across that lonely stretch of Siberian forest, the trees have grown back, but the story of what happened there still hangs in the air. The record of a dawn when the sky itself came undone. Denisova Cave, Altai, hybrid hominin and enigmatic artifacts. Deep in the Altai mountains of southern Siberia, where pine forests meet limestone cliffs, lies a cave that has changed what we know about human history. From the outside, Denisova Cave looks ordinary, a dark opening in a grey rock wall overlooking the Anui River. But inside its layers of dust and bone, scientists uncovered something extraordinary, the genetic echoes of a vanished branch of humanity. The story began in 2008, when Russian archaeologists sifting through layers of ancient sediment found a small fragment of finger bone from a young girl. It looked unremarkable, no larger than a breadcrumb, but when scientists sequenced its DNA, the results stunned the world. The genome did not match modern humans or Neanderthals. It belonged to a distinct group that had never been identified before. They were named the Denisovans, after the cave where they were found. Further excavations revealed more pieces, teeth, bone fragments and artifacts buried in layers spanning more than 300,000 years. The cave had been used by different hominin groups at different times, including Neanderthals, modern humans and Denisovans. But the layers did not neatly separate these groups. Instead, they overlapped, hinting at long periods of coexistence and contact. From this same cave in 2010, researchers uncovered another surprise: the bone of a teenage girl who carried DNA from both Neanderthal and Denisovan ancestors. She was a first-generation hybrid. Her mother was Neanderthal, her father Denisovan. No other site on Earth has yielded such a direct link between two distinct human lineages. This discovery proved that ancient human groups met and interbred, sharing genes and probably culture. The artifacts found in Denisova Cave add more complexity. Among the thousands of items are ornaments made from animal teeth, bone needles with drilled eyes, and a polished green stone bracelet that required techniques far beyond what many thought possible for that time. The bracelet, dated to around 40,000 years ago, is made of chloritolite, a material that had to be sourced from distant locations. Its surface is smooth, and the hole drilled through it shows spiral striations consistent with a high-speed rotary tool, something more advanced than any known Paleolithic technology of that period. This level of craftsmanship raises a difficult question: who made it? The layer in which the bracelet was found predates the arrival of Homo sapiens in the region, suggesting that Denisovans or possibly Neanderthals created it. Yet both species were thought to have simpler tool cultures. If the dating is correct, it would mean that these ancient humans had far greater cognitive and technical skills than previously assumed. Excavations in the cave revealed over 20 different sediment layers, each preserving fragments of time. Using radiocarbon dating, uranium series analysis, and stratigraphic modelling, scientists built a timeline stretching from around 300,000 years ago to the recent Holocene. Denisovans occupied the cave intermittently for tens of thousands of years. They shared it with Neanderthals, who lived there between roughly 130,000 and 80,000 years ago. Later, around 45,000 years ago, modern humans reached the region, possibly even meeting the last Denisovans before they vanished. The DNA evidence extracted from the sediments themselves confirmed this overlap. Even without visible bones, genetic traces in the soil revealed when different species lived in the cave. Denisovan DNA appeared in multiple layers, sometimes alongside Neanderthal signatures. These results show not just occupation but mixing, different human groups returning to the same shelter through shifting climates and ages. The Denisovan genome opened new doors in population genetics. Comparisons with modern humans revealed that Denisovans left their mark in our DNA. Populations in Melanesia, Australia, and parts of East and Southeast Asia carry up to 5% Denisovan ancestry. Some of these genes influence traits like high-altitude adaptation, helping Tibetans survive in thin air, proof that Denisovan genetics still shape human biology today. yet the physical identity of the Denisovans remains largely unknown. Apart from fragments, a finger bone, a few teeth, a skull piece, no complete skeleton exists. Their facial features, body proportions and skin colour can only be inferred from genetic modelling. Recent computational reconstructions suggest a broad face, robust build, and features blending Neanderthal and early modern human traits. But no one has ever seen a Denisovan skull intact. Inside the cave, the sediment layers hold more than fossils. They contain traces of pollen, charcoal, and microfauna that reveal the world these humans inhabited. Cold, steppe-like periods alternated with warmer interglacial phases. The cave served as a refuge through millennia of climate swings. The Denisovans hunted bison, woolly rhinoceros, and deer. They made tools from stone, bone, and ivory. Cut marks on animal bones show that they butchered their prey with skill, likely using complex hunting strategies. Even the microflora in the sediments tell part of the story. Spores and seeds show that the surrounding environment once shifted from dry tundra to forest, then back to open grassland. Each shift shaped who could survive there and when. Researchers continue to analyse minute details. The isotopic composition of bone fragments, the DNA of microscopic fibres, the magnetic properties of ash layers that show how often fires burned. The archive grows deeper with every layer studied. Still, the mystery of who the Denisovans were, how they looked, how they thought, and how they disappeared remains unresolved. Their genes live on in us, but their culture is known only through scattered objects and a handful of bones. In the quiet darkness of Denisova Cave, the echoes of those ancient lives linger, written in the dust and DNA of a species once forgotten by time. Malta boy, Mawan near Lake Baikal. A soft wind drifts across the frozen ground near Lake Baikal. Imagine the Siberian horizon 24,000 years ago, a time when humans lived in small bands beneath an icy sky. In that world walked a boy whose DNA would rewrite our picture of ancient migrations. He's known as the Malta boy, or MA1, his bones discovered near the village of Malta, northwest of Lake Baikal. Archaeologists first uncovered his remains in the 1920s. Decades passed before genetic science caught up. In 2013, scientists successfully sequenced a large portion of his genome. The results showed something unexpected. The Malta boy's ancestry was not purely East Asian, as many would have assumed for a Siberian individual. Instead, his DNA revealed a mix, a lineage now called Ancient North Eurasian, ANE. That lineage appears to bridge West Eurasia and the first peoples of the Americas. The Malta genome shares stronger affinities with modern Native Americans and Western Eurasians than with East Asians. In other words, part of the ancestral pool of the first Americans came from populations like MA1. Modern Siberian groups, especially in Western Siberia, trace a large percentage of their ancestry to ANE. For example, some studies estimate that the Mansi and Khanty peoples derive more than half their genetic heritage from connections to MA1 and similar lineages. At the same time, genes from East Asian populations contribute to the rest of their makeup. These crossroads of ancestry show that far northern Siberia was not a genetic dead end. It was a junction. One branch would drift east, another south, and part would cross the Bering Land Bridge into the Americas. The Malta boy is a key node in that branching, yet many puzzles remain. MA1's genome shows no East Asian component, which means that the mixing between AN and East Asian populations must have occurred later, after his time. Populations in Siberia and Asia today often combine both ANE and East Asian ancestry, but those combinations were not yet in place 24,000 years ago. We don't yet know how widespread ANE people were. Was the Malta boy typical in his region? Or was he part of a small enclave with distinct genetics? Other ancient Siberian individuals, like those from Afontova Gora, show a related ancestry, hinting at a broader ANE presence during and after the last glacial maximum. Also open is the timing and place of the admixtures. When exactly did ANE groups meet East Asian populations? And where did those meetings occur, deep in Siberia or farther south? Some models place the admixture events in parts of North Asia or in Beringia, as people move toward the Americas. Another question: how did MA1's descendants move? The genes linked to him spread not just east but west into Europe and south into Central Asia. That suggests migrations or population replacements over millennia. The ancient distribution of haplogroups, like mitochondrial U and Y haplogroup R, offers further clues, but they do not yet settle the map. His remains show he was a child, perhaps around 3 to 4 years old. Alongside his bones, archaeologists found evidence of the Malta barrette culture: stone tools, ivory ornaments, personal items. The culture demonstrates that his people were not primitive. They made polished bone tools, carved figurines, and managed raw materials skillfully. Their presence north of Lake Baikal during a time of harsh climate speaks to resilience and adaptation. From the sediments around Malta, pollen and charcoal layers record climatic shifts, cold dry periods followed by brief warming intervals. Those shifts may have influenced how people moved, where they settled, and how populations met. Genetic studies continue to refine the picture. Each new ancient DNA sample expands or challenges the model. Some instances show backflow, genes moving from later Siberian or East Asian people into ANE-derived groups. Others test models of ghost populations, groups that left no trace except through genetic mixing. Thus the Malta boy sits at a nexus. He links the deep past in Siberia with peoples far across the Pacific and westward into Eurasia. His life was brief, his legacy expansive. Ust Ishim femur, West Siberia. It began with a single bone found by chance along the Irtysh River in western Siberia. Local villagers discovered it in 2008, eroding from the riverbank near Ust Ishim, a remote settlement surrounded by endless forest and floodplain. To the untrained eye, it looked like any old fossil, but tests soon revealed that it was something extraordinary. A human femur roughly 45,000 years old, the oldest directly dated modern human ever found in northern Eurasia. The bone belonged to a man who lived during a time when ice sheets were growing across the northern hemisphere, yet Siberia was not the empty land it would later become. Patches of steppe stretched between birch and pine. Mammoths, horses and bison roamed the plains, and small groups of hunter-gatherers followed them. The man from Ust Ishim was one of these people, an early representative of Homo sapiens moving across Eurasia long before modern humans became established in Europe or East Asia. The discovery gained importance not for its shape, but for its DNA. Scientists at the Max Planck Institute extracted genetic material from the dense inner tissue of the femur and sequenced his entire genome. The results became a cornerstone in human evolutionary studies. His DNA confirmed that he was fully modern human, not Neanderthal, not Denisovan, but his genome carried traces of both. The length of those traces told an even deeper story. Embedded within his genome were segments of Neanderthal ancestry that were longer and less broken up than in modern people today. Over generations, DNA inherited from distant ancestors becomes chopped into smaller fragments through recombination. The length of these Neanderthal segments allowed researchers to estimate when his ancestors had interbred with Neanderthals. The calculation pointed to an event roughly 50 to 60,000 years ago. Just before his own lifetime, that finding fixed a timeline for when modern humans first met and mated with Neanderthals after leaving Africa. The man himself lived not long after those first crossings of genetic lines. His genome sits close to the root of all non-African humans, older than the separation between the populations that would later give rise to Europeans and East Asians. Yet he is not directly ancestral to either group. His lineage seems to branch off before their divergence, showing that early humans were already dispersing widely across Eurasia in complex overlapping waves. Radiocarbon dating placed the femur at about 45,000 years old, confirming the genetic age. The bone's preservation in permafrost allowed high-quality DNA extraction, rare for remains of such antiquity. Stable isotope analysis of nitrogen and carbon suggested a diet rich in meat, consistent with a hunter who relied on large mammals in a cold steppe environment. Microscopic study of bone structure revealed no signs of disease or injury. He likely died young, possibly before age 40. Yet despite the completeness of his genome, much about his life remains unknown. No tools, ornaments, or other artifacts were found with the bone. There was no burial context, no camp remains, only the solitary femur. Researchers cannot tell whether he belonged to a small isolated group or to a larger network of migrants spreading north from Central Asia. The routes they took into Siberia are still debated. Some may have followed river valleys from the west, others the steppe corridor that stretched across Kazakhstan. The Ust Ishim man's genome also offers a window into what humans looked like at the dawn of Eurasian expansion. Genetic markers suggest that he probably had dark hair and eyes, with skin pigmentation intermediate between early Africans and later Europeans. His genome lacks the later variants associated with lighter skin that became common only after tens of thousands of years in northern latitudes. What makes the find remarkable is its position in time, after modern humans left Africa, but before regional populations had differentiated. His genetic distance from any modern population is almost equal to that between Europeans and East Asians today. In that sense, he represents a snapshot of humanity before it splintered into the many branches we know. The Ust Ishim data also refine the timeline for Neanderthal extinction. Because he already carried Neanderthal DNA, and because Neanderthals vanished roughly 10,000 years after his lifetime, it means that these two human groups coexisted in Eurasia for millennia. The genetic exchange must have taken place somewhere in Western Asia or the Near East, and the echoes of that encounter travelled with his ancestors into Siberia. In his genome, scientists also searched for Denisovan traces, the genetic signature of another archaic population known from the Altai region farther east. Surprisingly, they found none, suggesting that his group had not yet reached that part of Siberia or had minimal contact with Denisovans. This absence helps chart the boundaries of ancient interactions between early human species. After the sequencing was completed, researchers compared his DNA to later ancient genomes from Europe and Asia. None matched directly, but fragments of his genetic legacy persist indirectly in later Eurasian populations through shared ancestry. His genome now serves as a baseline for studies on mutation rates, population splits, and migration speeds. By counting the number of new mutations accumulated since his lifetime, scientists refined the molecular clock used to estimate the timing of key evolutionary events. The femur itself rests today in storage at the Russian Academy of Sciences, safeguarded like a library of deep history. The data it contains continue to inform new studies, from mutation modelling to climatic adaptation. Its isotopic ratios, microstructures, and mineral composition are still being analysed to reconstruct the environment in which the man lived. The ground around Ust Ishim remains largely unexplored. Each new core sample from the Irtysh basin might reveal more about the world he inhabited, a landscape of cold rivers, mammoth herds, and humans just beginning to understand the vastness of the continent they had entered. His single bone carries evidence of one of the earliest chapters of our species in Siberia, a solitary clue linking modern humanity to the deep record of the Ice Age plains, Ice Maiden of the Altai, Pazyryk culture. A cold mist drifts over the Yukok Plateau in Altai. Imagine a time when snow lay thick, and beneath it rested a woman frozen in silence for 2.5 millennia. She would come to be known as the Ice Maiden, a Pazyryk princess whose body preserved in ice revealed a startling bridge to ancient Siberia. In 1993, Russian archaeologist Natalia Polosmak led an expedition to a remote, previously untouched burial mound, or kurgan, in the highlands near the Mongolian border. Under layers of stones and earth, her team uncovered a subterranean wooden chamber built with logs and insulated carefully. Within it lay the wrapped body of a young woman seated on her side, accompanied by 6 sacrificed horses. The tomb had at some point flooded with freezing water, then froze solid over the centuries, preserving the chamber like a crypt in ice. The coffin was carved from the trunk of a Siberian larch, adorned with leather appliques of deer and snow leopards. The woman wore a felt headdress nearly a metre tall, intricately worked to display animals and mythic forms. Her clothing, a red and white striped wool skirt, a blouse made of yellow silk, high white felt leggings and marten furs. Near her remains lay vessels, food remains, and coriander seeds. All this carefully arranged, a ritual burial in full ceremony. When Polosmak's team exposed the body, the preservation stunned them. Skin, soft tissue, tattoos, all remained intact. On her left shoulder, a deer motif with flowing antlers rooted into floral spirals. On her wrist and thumb, more figurative animal designs. The ink had not vanished, though faint, visible as patterns of darker skin against pale tissue. Her body, carefully embalmed with peat and bark, appeared sleeping, as though merely resting. Modern imaging techniques have since enhanced and revived the visibility of her tattoos. Infrared photography reveals lines and shading too subtle for the naked eye. Researchers have found that the tattoos display animal forms, stags, griffin-like beasts, perhaps mythical creatures, intertwined in motion. The uniform thickness of many lines suggests a practiced hand and deliberate tools. Some lines were made by multi-point methods, others by single-point tools. The overlaps hint at where the tattooist paused and resumed work, revealing aspects of the process. The forensic reconstruction of her physical state offers clues to her life and death. Estimates place her age between 20 and 30. Her scalp was shaved, but she wore a wig beneath the headdress. Bone studies show no major trauma, but some suggest she may have carried internal illness or suffered from disease. A 2014 study proposed she might have had breast cancer, worsened by injuries from a fall. The combination of illness, instability, or conflict may have played a role. Some bones show microfractures consistent with blunt impact or a fall, though whether before burial or in ritual handling remains uncertain. Her posture, the arrangement of grave goods, and the scale of the tomb suggest high status, possible religious or clan significance. Some scholars propose she was a priestess or noble leader within Pazyryk society. Yet the signal must be extracted from the noise. Her tattoos, while striking, cannot alone confirm identity or social rank. The lack of written records or inscriptions means interpretations must rest on context and comparative analysis. Some see the deer and animal motifs as shamanic symbols. Others believe the forms connect with tribal totems or protection rites. But the deeper meaning eludes certainty. Controversy shadows aspects of her excavation and later treatment. Critics argue that the methods used to melt ice and extract the body risked damage. The process of transporting her remains suffered mishandling and deterioration. Local Altai groups consider the Ice Maiden their ancestor. She became a symbol of identity and heritage. Disputes arose over whether she should remain in Novosibirsk or return to Altai. Indigenous voices claim her remains belong to the land, cautioning against foreign study without respect. Genetic testing adds more questions. Early DNA work from her remains indicated European affinities. Some Russian scientists argued she belonged more to European populations than to modern Altaians. That finding strained relations, as local groups rejected claims that she was external to their heritage. Later tests show more complexity, with unique alleles and no clean alignment with contemporary Altaian genetics. Dating of her tomb, through dendrochronology of the logs and radiocarbon analysis of artifacts, places her death in the 5th century BCE, well within the period of Pazyryk culture. That culture is itself part of the Scytho-Saka nomadic world, tied by art, trade and migration across Central Asia. The Pazyryk culture is also known for other tattooed mummies and richly adorned burials across Altai and northern Mongolia. Artifacts from her tomb demonstrate extensive trade links. The silk may have come from Central Asia. The felt and leather show advanced craftsmanship. The vessel materials, decorative elements, and symbol forms parallel motifs found as far as Persia or the Iranian plateau. Her burial is not an isolated marker, but part of a network of exchange, mobility, and cultural contact. Still, many who study her caution against bold claims. The tattoos suggest advanced technique, but we lack the actual tattooing tools from her chamber. The epidemiological inferences about her health are speculative. The genetic signals are partial and may degrade with contamination. Her tomb, though elaborate, is a solitary mortuary specimen. How representative she was of her society we cannot know. The Ice Maiden remains a haunting presence. Not merely a corpse, but a storyteller's fragment. Her body speaks in ink and wood, in fur and metal, in preserved flesh and ancient soil. She offers glimpses of status, ritual, aesthetics, health, and death among magno-steppe nomads. But her story remains stitched with uncertainty, a voice from 2,500 years past, filtered through ice, excavation, and human desire to know. Deer stones and Okunev steppe stelae, Tuvakakasia. Across the open steppe of southern Siberia, tall stone figures stand in silence. They are weathered by wind and frost, but their carvings still glow in the low light. Graceful deer with elongated bodies and antlers that curl into spirals, rising like flames. These are the deer stones of Tuva and Khakassia, monuments that have watched over the grasslands for nearly 3,000 years. They appear alone or in groups scattered across Mongolia, southern Siberia, and parts of Central Asia. Each stone is upright and slender, often 2 to 4 meters tall, carved from granite or sandstone. The front faces bear intricate engravings: flying deer, belts with weapons, sun discs, and geometric bands that trace the outline of a body. In some cases, faces are faintly visible, eyes marked by hollow circles, mouths by a single line. The craftsmanship varies, but the imagery follows patterns. The deer always appear in motion, as if leaping through air. Their legs fold under them, and their antlers flow backward into curling branches or flame-like motifs. Some stones show multiple deer stacked vertically, their bodies curving upward toward the top. Others depict daggers, axes or mirrors, objects linked to warriors or ritual specialists. Beneath the carved belts, horizontal lines may represent clothing or armour. Scholars have long debated what the stones mean. The most common idea is that they served as funerary markers, memorials for important individuals of nomadic societies in the Late Bronze Age. Excavations around several stones revealed burials or stone circles, suggesting they marked tombs. The images of deer might symbolize the soul's flight to the sky, a passage into another world. In steppe cosmology, deer were sacred animals, linked to the sun, movement and rebirth, but not all deer stones stand near graves. Some rise in open plains, unconnected to any burial. In these cases, they might have served as territorial markers, or as ritual centres where herders gathered for seasonal ceremonies. Others could be astronomical. Their alignment with cardinal directions and solstice points suggests intentional placement for tracking celestial cycles. Archaeologists studying shadow lengths and horizon lines at certain sites found correlations with sunrise and sunset positions. Whether those alignments were symbolic or functional remains open. The artistic style of the carvings reveals cross-cultural links. The deer motifs echo designs found on metalwork of the Scythian art style, which spread across the Eurasian steppe in the early Iron Age. Yet the deer stones predate that culture, hinting that the iconography originated here in the Altai and Sayan region. Some stylistic elements, spiral antlers, the flying posture, appear later in Scythian gold ornaments and saddle decorations, suggesting the stones inspired a broader visual language that followed nomadic migrations. Around Tuva and Circassia, other standing stones, often called Okunev stelae, carry different motifs. The Okunev culture, older than the deer stone builders, flourished around 2500 BCE in the Minnesota Basin. Their stelae depict human-like figures with large circular eyes, solar symbols, and abstract geometries. Many feature rows of faces stacked vertically, their expressions ambiguous, part human, part cosmic. The Okunev stones are thick, block-like, and carved in low relief. Some show arms extended, hands open, as if in prayer or invocation. Others contain concentric circles and zigzag lines, interpreted as suns, lightning, or energy. Excavations at Okunev burial sites show that these stones stood beside tombs aligned with specific directions. The solar symbols and anthropomorphic forms suggest a belief system centered on celestial order, life cycles, and transformation after death. The relationship between the Okunev stelae and the later deer stones is debated. Some archaeologists see continuity, a shared steppe tradition evolving over centuries. Others propose independent origins linked by trade and migration. The gap in time and style complicates direct connections, but both traditions share a fascination with sky, movement, and the merging of animal and human forms. Despite their prominence, the tools and methods used to carve these monuments remain uncertain. Microscopic analysis of grooves shows that bronze chisels or stone tools were used, with fine polishing by sand abrasion. The work required skill and planning. The stones were quarried, transported, and shaped with deliberate effort. Many were placed in groups of 3 or 4, sometimes surrounded by smaller slabs forming an enclosure. When field researchers map their positions, patterns emerge. Clusters appear along river valleys and mountain passes, often where trade or migration routes crossed. These landscapes were liminal zones, boundaries between tribes, pastures, or seasonal territories. The stones may have acted as anchors in the nomad's mental geography, physical links to ancestors or celestial forces that govern time and space. In the 20th century, surveys catalogued over 1,200 deer stones across Mongolia, Tuva, and the Sayan region. Laser scanning and photogrammetry now capture their surfaces in detail, allowing comparisons of style and technique. Some researchers identify regional schools of carving, the Mongolian, Saiyan Altai, and Trans-Baikal types, each with distinct artistic conventions and tool marks. Yet the interpretation of meaning remains tangled between data and myth. Soviet-era archaeologists favoured materialist explanations, framing them as markers of social hierarchy or clan identity. Later researchers reintroduced symbolic and cosmological readings, seeing in the carvings a coded system of beliefs about death and transformation. Ethnographic parallels among Turkic and Mongolic peoples support the idea of deer as a mediator between worlds, a spirit guide for the soul. Archival drawings from early explorers like Radlov and Talgren, along with 19th century travel notes, provide a visual record of stones now damaged or lost. Modern documentation continues this work, combining satellite mapping with ground verification to monitor erosion and vandalism. In some cases, fragments have been moved to museums in Kizil, Abakan and Ulaanbaatar, though many still stand exposed on the open plains. The debate over purpose continues. Are these monuments portraits of warriors, celestial calendars, or sacred totems? Each interpretation finds partial support, yet none fully resolves the puzzle. The stones keep their silence, their deer still running skyward across their weathered faces, while the steppe winds pass through as they have for thousands of years. Altai megaflood relics, Chuya-Kurai basins. The Altai mountains rise like a spine through the heart of Central Asia, a maze of valleys and glacial basins shaped by forces that once moved faster than any river on Earth. Here, across the Chuya and Kurai basins, the land still bears the marks of a catastrophe so immense that even mountains seem to have remembered it. From the ground, the valleys look calm, rolling fields and scattered hills, but from the air, patterns emerge, vast ridges arranged like waves frozen in motion. Each ridge stands 10, sometimes 15 meters high, spaced evenly apart, running for kilometers. These are giant current ripples, relics of ancient floods that tore through the Altai at the end of the last ice age. They are not dunes or wind-shaped hills, they are the footprints of water moving with the force of an ocean. Geologists first recognized their true nature in the 1960s. Comparing the scale and spacing of these ridges with smaller river forms, they realized that such structures could only have been carved by immense volumes of fast-moving water. Subsequent fieldwork confirmed cross-bedded gravels, coarse sediments and scoured bedrock, all signs of catastrophic flow. The culprit was ice. During the late Pleistocene, glaciers advancing from the Altai peaks dammed valleys and trapped enormous bodies of meltwater. The largest of these, known as Glacial Lake Kurai-Chuya, filled the intermontane basins between the Chuya and Kurai ridges. At its maximum, the lake may have reached volumes of several hundred cubic kilometers, comparable to one of today's Great Lakes. Then, sometime between 15,000 and 13,000 years ago, the ice dam failed. Whether by melting from below, cracking under pressure, or sudden destabilization, the barrier gave way. When it broke, the water released in a torrent that dwarfs any known modern flood. The flow rushed through the mountain corridors at speeds estimated over 100 kilometers per hour. The wave carved deep gorges, stripped soil from slopes, and slammed into valley walls with the power of millions of cubic meters per second. In the Chuya Basin, floodwaters rose hundreds of meters, depositing gravel bars as big as city blocks. Downstream, near the Katun Valley, they left scoured bedrock surfaces polished smooth by turbulent flow. Boulders weighing hundreds of tons were rolled like pebbles. In 2009 and later studies, satellite and drone mapping revealed compound flood deposits, multiple ripple sets stacked at different elevations. That suggests the flooding was not a single event, but a sequence of outbursts. Some lakes may have reformed behind ice barriers and failed again, perhaps several times within centuries. Each burst added new layers of erosion and sediment, reshaping the landscape. Forensic reconstruction begins with the evidence. The ripple crests are oriented along the valley's flow direction, spacing consistent with subaqueous dunes scaled to water depth of 100-200 meters. Sediment analysis shows well-sorted gravel and sand, features of high-energy transport. Potholes in bedrock, called colks, mark vortices powerful enough to drill into stone. On cliffs, scientists find polished benches where floodwaters once climbed hundreds of meters high. Radiocarbon dating of organic material buried within flood sediments provides a timeline. Most dates cluster near the terminal Pleistocene, aligning with regional deglaciation. Yet the ages vary enough to imply several pulses of flooding rather than one collapse. Ice cores and global sea level records show synchronous warming periods that might have destabilized glacier dams across Siberia. Comparisons with other mega-flood sites, such as the channeled scablands in North America, reveal striking parallels. Both landscapes feature giant ripples, erosional canyons, and gravel deposits shaped by sudden releases of glacial lakes. The Altai floods, however, occurred in rugged mountain terrain, where confinement amplified flow energy. The search for triggers continues. Modelling studies explore whether climatic warming, seismic activity, or gradual subglacial drainage initiated the final breach. Field evidence hints that meltwater accumulation beneath the ice dam may have raised pressure until hydrofracture tore through the barrier. Once a crack formed, the failure was instantaneous. Yet uncertainties persist about lake volume and recurrence. Estimates range from 600 to 1,200 cubic kilometres. Some reconstructions propose at least 3 major floods separated by intervals of lake reformation. Others suggest smaller outbursts followed by one terminal megaflood. Remote sensing data help refine these models, but erosion has erased many key markers. At the crossroads of geology and climate, these floods also shaped ecosystems and migration routes. The release of such massive volumes of cold freshwater into downstream valleys could have altered local climates and biotic recovery after the Ice Age. Some researchers speculate that flood corridors later served as migration pathways for animals and humans moving through the Altai region once the waters receded. Fieldwork continues each summer. Scientists hike along ripple crests, dig trenches into gravel bars, and scan terraces with LiDAR. Each dataset refines the hydraulic models: how deep the water was, how long the floods lasted, how far they reached. Some simulations show water levels temporarily submerging entire valleys that today lie far above river level. What remains on the surface is a geological record frozen in scale, evidence of energy and speed few natural forces can match. The Chuya and Kurai basins preserve the signatures of these vanished floods better than almost anywhere else on Earth. The ground itself is a fossil of motion, the record of when ice and water collided and the mountains stood in the path of something unstoppable. Chara Sands' Siberian desert, Baikal. In the middle of the Siberian taiga, where endless pine forests stretch to the horizon, lies a patch of golden sand that looks wildly out of place. It's called the Chara Sands, a miniature desert surrounded on all sides by snow-capped mountains, rivers, and dense boreal woodland. From above, it appears like an island of dunes floating in a sea of green. This strange landscape sits in the Baikal region, near the town of Chara, more than 900 kilometers from Irkutsk. It covers roughly 50 square kilometers, with dunes rising as high as 80 meters. They shift and ripple with the wind like those in the Gobi or Sahara, yet winter temperatures here can drop below -40 degrees Celsius, and snow covers the ground for half the year. The existence of a desert in one of the coldest and wettest parts of Siberia defies first impressions. From the ground, it feels surreal. The sand is fine-grained and warm in summer sunlight, bordered by birch and larch forest. Beyond that rise the Kodar Mountains, their ridges still holding ice and glaciers. To stand among the dunes is to witness a contradiction of climate and geography, a relic of an older world persisting where it shouldn't. Scientists have spent decades trying to understand how the Chara Sands formed and why they still survive. Their shape and composition suggest that they are not the product of modern desertification, but rather relic deposits from a much earlier period, when water, not drought, shaped the landscape. Sediment analysis shows that the sand grains are mostly quartz and feldspar, rounded and sorted by both wind and flowing water. Beneath the dunes lie layers of gravel, clay, and silt, evidence of an ancient river system. Geological mapping points to the Chara River and its tributaries as the main architects. During the late Pleistocene, as glaciers melted and retreated from the Kodar Range, huge floods and braided rivers swept through the basin, depositing massive amounts of sediment. Over time, the wind took over, reshaping the exposed material into dunes and ridges. The sand itself dates back thousands of years. Thermoluminescence dating and stratigraphic sampling indicate that the active dune field formed roughly 20,000 to 12,000 years ago, around the end of the last ice age. As glaciers retreated and rivers dried or changed course, wide sandy floodplains were left behind. With fewer plants to anchor them in the cold, dry post-glacial climate, the sands began to move, driven by katabatic winds spilling from the mountains. But how do these dunes persist today, in a region that receives significant rainfall and supports thick forest? The answer lies in a delicate balance of local conditions. The Chara Basin is encircled by mountains that create a rain shadow effect. Moisture from the west and south is partially blocked, leaving a pocket of relatively dry air within the basin. Summer months are windy and warm enough to dry the sand surface quickly, while winter freezes the upper layers, preventing complete stabilization by vegetation. Field observations show that the dunes move very slowly, in some areas only a few centimeters per year. The edges of the sand field are gradually being invaded by pine and birch roots, suggesting that forest is reclaiming ground. Yet, despite this encroachment, the desert endures. Seasonal cycles of thawing, drying and wind erosion keep parts of the surface active. In some spots, the dunes reveal a phenomenon called cryogenic layering, where freeze-thaw cycles form patterned ground and polygonal cracks beneath the sand. This interaction between permafrost and aeolian processes makes Chara unique. It's not a hot desert at all, but a cold one, shaped by the same winds that once carried glacial dust across Eurasia. Researchers studying its microclimate have recorded extreme variations in surface temperature. On a summer afternoon, sand temperatures can exceed 40 degrees Celsius, while air just above the dunes remains near 20. At night it drops sharply, sometimes below freezing even in July. These fluctuations affect how the sand crust forms and breaks apart, influencing how wind redistributes grains. The Chara Sands also serve as a natural laboratory for studying paleo-environmental change. Cores taken from beneath the dunes contain traces of pollen and organic material, allowing scientists to reconstruct past ecosystems. They reveal a sequence of transitions, from cold glacial tundra to steppe, then to forest, each leaving a signature in the sand's chemistry and texture. This makes Chara one of the northernmost examples of a preserved Ice Age sand system. There's also evidence that groundwater plays a role in maintaining the dune field's shape. Below the surface, layers of frozen and unfrozen sediment interact with shallow aquifers. In spring, meltwater saturates the lower layers but quickly drains, leaving upper surfaces dry enough for wind transport. In winter, ice layers form barriers that limit moisture infiltration, preserving the dune structure through freezing months. Remote sensing and satellite imagery have helped chart the dunes' evolution. Comparison of aerial photos from the 1960s with modern images shows minor shifts in dune crests and expansion of vegetation margins, but the main body remains stable. Some recent modelling suggests that climate warming could alter the balance, reducing permafrost depth and changing wind regimes, but for now, the desert still breathes within the forest. Standing atop the tallest ridge, one can see the contrast. Golden sand below, black-green forest beyond, and the glacial peaks of Kodar rising above both. The sound is of wind moving across grains that once lay in ancient riverbeds. The Chara Sands are not a mirage, nor a product of aridity. They are the memory of water, frozen into a desert that should not exist. Lake Baikal methane pockmarks and seep fields. Far below the frozen surface of Lake Baikal, where sunlight fades into darkness, the floor of the world's deepest lake is alive with movement. In this cold, pressurized world, gas bubbles rise from the mud, drifting upward through this water column in long, trembling strings. These are methane seeps, part of a hidden system that connects the geology, chemistry, and biology of Baikal in ways still not fully understood. Baikal stretches more than 600 kilometers through southern Siberia, reaching depths over 1,600 meters. It holds 1/5 of all the planet's unfrozen freshwater, yet beneath its calm surface it is geologically restless. The lake sits inside a continental rift, an active zone where the Earth's crust slowly pulls apart. This deep fracture allows heat and fluids to rise from the subsurface, creating one of the most dynamic freshwater ecosystems on Earth. Scientists first detected methane release from Baikal sediments in the 1980s while studying its unique bottom fauna. Sonar surveys revealed plumes of bubbles escaping from the lake floor, some forming shimmering curtains that stretched upward for tens of meters. Subsequent dives by research submersibles confirmed hundreds of these vents, especially along the central and southern basins. The most striking feature on the lakebed are the pockmarks, crater-like depressions formed where gas escapes explosively or persistently over time. Some measure a few meters across, others exceed 100 meters in diameter. The rims often rise above the surrounding sediment, while their centers may contain active vents or hydrate crusts. These structures are common in marine environments, but Baikal is unique. It is the only freshwater lake known to host extensive methane hydrate deposits and seep fields. Methane hydrates are crystalline solids, ice-like cages that trap gas molecules under pressure and low temperature. They form within sediment layers hundreds of meters beneath the lakebed, stable only under precise conditions. When those conditions change, through temperature shifts, seismic activity, or sediment slumping, the hydrates can break down, releasing gas into the water. In Baikal, the interplay between tectonics and climate makes the system particularly active. Fault zones at the bottom of the lake act as conduits, allowing methane-rich fluids to migrate upward. Earthquakes periodically shake these pathways open. At the same time, climate variations influence lake temperature and pressure gradients, subtly altering the stability of hydrate layers. When gas escape intensifies, it scours the lake floor, carving new pockmarks and reshaping old ones. Field studies using sonar imaging and remotely operated vehicles have mapped more than 1,000 pockmarks and vent sites. The most active areas cluster along the Selenga Delta, the Pozolskaya Bank, and the Akademischen Ridge, regions where sediment thickness and fault activity intersect. Here, continuous streams of bubbles rise from the bottom like underwater geysers. Some vents are steady, others pulse rhythmically, modulated by small pressure changes or microseismic events. Water samples taken above these sites show elevated concentrations of dissolved methane and other hydrocarbons. Yet despite this intense local activity, Baikal's overall methane flux to the atmosphere remains modest. The reason lies in the lake's biology. Methane-oxidizing bacteria flourish around seeps, forming mats and biofilms that consume most of the gas before it reaches the surface. This microbial filter transforms methane into carbon dioxide, which dissolves in the water, reducing greenhouse release. Sediment cores reveal how long this process has been active. Layers rich in organic carbon, sulfides and microfossils trace the waxing and waning of seep fields over tens of thousands of years. Radiocarbon dating of carbonate crusts, formed when methane reacts with dissolved minerals, shows ages spanning from a few centuries to more than 10,000 years. The flux, it seems, rises and falls with both tectonic and climatic rhythms. Researchers also study the chemistry of gas hydrates themselves. Samples retrieved from deep drilling projects show that Baikal hydrates contain unusually pure methane, derived mostly from microbial decomposition of organic matter buried in sediments. In contrast to oceanic hydrates, which often contain mixed gases from deeper thermogenic sources, Baikal's are biologically generated. Yet some isotopic signatures point to minor contributions from deeper reservoirs connected to the rift's mantle heat flow. The lake's seismic activity adds another layer of complexity. Small earthquakes regularly strike along the fault zones. In some cases, researchers recorded increased gas venting immediately after such events, suggesting that even minor ground motion can release trapped methane. Conversely, over time, fine sediments may seal vents until pressure builds again. The pattern is cyclical, quiet accumulation followed by sudden release. These subsurface processes may also connect to phenomena visible from above. Some scientists have proposed that the mysterious ice rings appearing on Baikal's surface in late winter could be linked to underlying methane seeps. Rising warm water from gas-driven convection might thin the ice, creating circular patterns detectable from satellites. While not every ring aligns with a seep field, the coincidence in several cases keeps the hypothesis alive. Modern monitoring combines sonar mapping, seismic sensors, and satellite data to track how gas release zones evolve. High-resolution bathymetry has revealed new pockmarks forming within just a few years, proof that the landscape beneath Baikal is still changing. Drone and ROV footage show microbial mats waving in the currents, gas streams twisting through columns of clear water, and white hydrate nodules embedded in the mud. Despite decades of research, key questions remain. how stable are Baikal's hydrate deposits under current warming trends? Will increasing regional temperatures shift the equilibrium, leading to larger methane releases? And what role do these subsurface emissions play in the lake's nutrient cycles and biodiversity? Each season brings new measurements. Scientists return with submersibles and sediment corers, probing deeper into the hidden architecture of the lake. The picture that emerges is one of constant motion. Gas, ice, microbes and water intertwined in an ancient system still learning to adapt to a changing planet. Beneath the mirror surface of Baikal, the past and present of the Earth's atmosphere are quietly connected through the faint rising shimmer of methane bubbles. Zhokov Island, high Arctic, earliest dog sledding. Far to the north, where the Arctic Ocean turns to drifting ice, lies a small island called Zhokov, part of the DeLong archipelago off Siberia's northern coast. It is a place few humans have ever seen, an isolated rise of frozen tundra battered by wind and fog. Yet beneath its permafrost lies one of the most revealing archaeological sites in the Arctic, the remains of a community that lived here almost 10,000 years ago, when the world was just emerging from the last ice age. The camp they left behind tells a story of adaptation, ingenuity and partnership between humans and animals that would transform survival in the north. Excavations on Zhokov Island uncovered hundreds of artifacts, bone tools, hunting weapons, worked ivory and, most strikingly, dog bones carefully buried near the dwellings. Genetic and morphological studies now suggest that these dogs were among the earliest known sled dogs in human history. The site was discovered in the 1980s by Russian archaeologists led by Vladimir Petulko, and systematic excavations began soon after. What they found was astonishingly well preserved. The permafrost had sealed entire layers of ancient life, traces of wooden structures, hearths, stone tools, and even footprints in the frozen soil. Radiocarbon dating placed the occupation at around 9,500 years before present, during the early Holocene. At that time, Zhokov was not yet a true island. Lower sea levels connected it to the Siberian mainland by a broad plain that stretched across what is now the East Siberian Sea. People living here were specialized Arctic hunters. Their tools and bones show they targeted reindeer, polar bears and Arctic foxes, and even occasionally hunted mammoths that still roamed the mainland's cold grasslands. They used composite weapons with detachable tips, carved from mammoth tusk and bone, evidence of sophisticated hunting strategies and engineering skill. Among the animal remains, however, researchers found something unexpected. Dozens of dog skeletons in distinct burials. The bones showed careful selection and management. Measurements of limb proportions and skull shapes indicate that these were not wolves, nor wild hybrids, but domesticated dogs bred for specific purposes. Some individuals were smaller and lighter, likely used for herding or companionship, while others were larger, stronger, and built for pulling loads. Detailed isotopic analysis of their bones revealed diets different from those of wild canids. The dogs ate food prepared by humans, including fish and reindeer meat. This dietary link points to deliberate feeding and care, not random association. Moreover, the pattern of wear on their teeth suggests that some animals regularly wore harnesses or mouth restraints, signs consistent with sled pulling. Genetic sequencing from preserved teeth confirmed that these dogs were part of a distinct northern lineage, ancestral to modern Arctic breeds such as the Siberian Husky, Alaskan Malamute, and Greenland sled dog. Their DNA shows early divergence from other domesticated dogs, possibly as far back as 15,000 years ago, but by the time of Zhokov they had already adapted to Arctic conditions. Thick coats, compact bodies, and efficient metabolisms suited for endurance in extreme cold. This makes the Zhokov site a milestone, the earliest direct evidence of organised sled dog transport. The discovery suggests that by 9,500 years ago, humans in Siberia were already using teams of trained dogs to move across ice and tundra, carry supplies, and hunt over long distances. Such a system would have expanded their mobility dramatically, allowing access to resources scattered across vast Arctic plains. The archaeological record also preserves indirect hints of this technology. Long bones carved into smooth shafts may have served as sled runners or frame components. Antler pieces shaped into loops or junctions could have functioned as harness fittings. While no complete sled survived, The combination of artifacts and animal evidence paints a clear picture of a culture that understood traction and team control. The partnership between humans and dogs at Zhokov represents an evolutionary crossroad. For the animals, domestication selected traits for strength, obedience, and cooperative behaviour. For the people, it created a tool that reshaped how they interacted with their landscape. Together, they formed a symbiotic system, humans providing food and shelter, dogs providing transport, protection, and hunting assistance. Climatic data from sediment cores around Zhokov show that this period marked the transition from glacial to interglacial conditions. The landscape was cold, dry, and windswept, dotted with sparse vegetation. Herds of reindeer migrated through the plains while sea ice advanced and retreated seasonally. In this setting, dog sledding was not a convenience but a necessity, a survival innovation that bridged scattered hunting grounds and allowed movement when snow covered everything. Later, as sea levels rose and the island became cut off from the mainland, the people of Zhokov moved south, carrying their technology with them. The tradition of Arctic sled dogs would persist for millennia, spreading across Siberia, Beringia, and eventually into North America with migrating groups. Modern DNA comparisons between ancient Zhokov dogs and those used by Inuit and Chukchi peoples show strong continuity, suggesting that the sled dog lineage endured through multiple waves of human migration. At the site today, archaeologists continue to recover fragments of wood, ivory, and bone that refine the story. Each season's thaw exposes more of the ancient settlement, but also threatens it. Warming temperatures accelerate permafrost melt, eroding layers that have been preserved for thousands of years. The discoveries at Zhokov link biology, archaeology, and climate history into a single narrative, a moment when humans and animals learned to master the frozen north together, leaving behind traces now emerging from the ice once again. Wrangel Island's last mammoths near 4000 BP. In the far Arctic Ocean beyond the Siberian coast lies Wrangel Island, a cold, windswept land of tundra, gravel ridges, and polar bears. But 4,000 years ago, it was home to the last known mammoths on Earth. While their relatives vanished from the mainland long before, a small herd survived here, isolated on this remote island long after the pyramids of Egypt had already been built. The mystery is not why they lived so long, but why they suddenly disappeared. The story of Wrangel's mammoths begins at the end of the last ice age. As the glaciers retreated, rising seas flooded the lowlands of Siberia. Around 10,000 years ago, Wrangel became an island, trapping a small population of woolly mammoths that had wandered north. Cut off from the mainland, they adapted to their new environment, a treeless landscape of sedges, dwarf willows, and icy rivers. The cold that once ruled the steppe still lingered here, giving them refuge while their mainland kin went extinct. For millennia, the Wrangel mammoths endured. Bones and tusks scattered across the island show that they remained abundant until roughly 4,000 years ago, nearly 6,000 years after the last mainland herds died out. The youngest known mammoth fossils, dated by radiocarbon, placed their final presence around 2050 BCE. At that time, human civilizations in Mesopotamia and Egypt were already writing their histories, but in the Arctic, these creatures still walked the frozen soil. For a long time, scientists assumed their isolation was a slow death sentence. With a small founder population and no new genetic input, inbreeding seemed inevitable. Early genetic studies revealed extremely low diversity in their DNA. Certain genes had accumulated harmful mutations, others were missing entirely. The island's small population, perhaps only a few hundred individuals, would have suffered from what geneticists call mutational meltdown, where errors accumulate faster than natural selection can remove them. One famous study even found evidence of strange mutations in sensory genes, including those affecting smell and coat colour. The Wrangel mammoths may have had altered sense, brittle hair, or fertility issues. This genetic decline led to the idea that their extinction was gradual and genetic, a slow fading out under the weight of bad DNA. But recent research has complicated that picture. In 2024, a new genome study comparing Wrangel mammoths with earlier Siberian and Alaskan specimens revealed that, while their genetic diversity was low, it was not catastrophic. Many essential genes were still functioning normally. The population had stabilized at a small size, but it was viable. That means they might have lived much longer if something sudden hadn't intervened. Archaeological and environmental clues hint at what that might have been. Around the same time as their disappearance, lake sediments on Wrangel Island show chemical signatures of abrupt environmental stress. The sulfur and carbon ratios in the layers suggest a possible extreme storm or flooding event, strong enough to disrupt freshwater systems and destroy food sources. Such an event could have contaminated lakes with salt water, leaving the animals without drinkable water for months. Another hypothesis points to disease. The isolation that once protected the mammoths could have made them vulnerable to a pathogen introduced by birds, humans, or other animals arriving on the island as sea ice shifted. Even a mild infection could have spread rapidly in a small genetically uniform herd. So far, no direct traces of disease have been found in the bones, but microbial DNA preserved in sediments is now being tested for signs of pathogens. There's also the human question. Stone tools and ancient sites have been discovered on Wrangel Island dating to roughly the same period. While there's no firm evidence of hunting, contact cannot be ruled out. A few mammoth bones show cut marks that might be human-made, though erosion complicates interpretation. Hunters reaching the island by boat or across winter ice could have disturbed the fragile population, even unintentionally, by taking freshwater sources or altering migration paths. Whatever the trigger, the end came quickly. Fossil layers show no gradual decline. No shrinking of body size, no thinning of bones, no long fade into extinction. The youngest bones lie just above layers rich in pollen and organic matter, and then, suddenly, there's silence. The mammoth's presence vanishes from the island's record almost instantaneously. The genetic evidence also suggests the final herd died out within a few generations. Unlike other species that show gradual replacement, Wrangel's mammoths left no trace of hybridization or migration afterward. It's as if the entire population vanished in one blow. That abruptness has led scientists to suspect an external shock, something beyond slow evolutionary decay. A storm, a pathogen, or a chain of events that erased the last pocket of survival. Today, Wrangel Island is a protected nature reserve, home to polar bears, musk oxen, and Arctic foxes. The tundra still hides bones of mammoths, many perfectly preserved by permafrost. DNA from these remains continues to tell their story, each sequence adding to the map of what went right and what went wrong. Samples of tusk collagen and bone microstructure reveal that, in their final centuries, the mammoths were smaller than their Ice Age ancestors, averaging about 2 meters at the shoulder. Yet isotopic analysis of their diet shows that they were eating well. Grasses, sedges and willow twigs, the same foods their ancestors preferred. There's no sign of starvation or environmental collapse. The silence that follows their disappearance remains one of the Arctic's most haunting mysteries. The island that saved them also became their last refuge. And though their DNA carries the scars of isolation, it doesn't tell the full story of why the world's final mammoths fell, only that they lived long enough to witness the dawn of recorded human history, before the cold wind of Wrangel blew over them for the last time. Viral time capsules in permafrost. Deep beneath the frozen ground of Siberia, the ice is not entirely dead. Locked within its layers are remnants of ecosystems that vanished tens of thousands of years ago. Plants, animal bones, pollen, bacteria, and as it turns out, viruses. Not just fragments of genetic code, but intact infectious particles that have survived in permafrost since before the rise of civilization. The discovery first emerged in 2014, when a team of French and Russian scientists drilling in northeast Siberia thawed samples of ancient soil taken from a 30,000-year-old layer. Under the microscope, they observed something unexpected. Massive virus particles larger than many bacteria, still able to infect their original hosts, single-celled amoebas. They named it Pithovirus sibericum, and later found another, Mollivirus sibericum, in nearby layers. Both remained dormant since the Ice Age, revived only when researchers exposed them to modern cells under controlled laboratory conditions. These giant viruses are not like the pathogens we normally think of. Measuring up to 1.5 micrometers in length, they are visible under a light microscope and carry hundreds of genes, far more than typical viruses. Some of their genes are unlike any known in the modern biosphere, suggesting long-lost branches of viral evolution. The realization that such organisms could persist for tens of millennia under frozen soil changed how scientists view biological survival in extreme environments. Since then, the search has widened. Permafrost cores collected across Siberia, from the Kolyma lowlands to the Lena River basin, have yielded a growing archive of ancient viral material. Some samples contain DNA fragments of viruses that infected mammals, plants or fungi, though only a handful have been successfully revived in the lab. Each discovery raises the same question: how many of these frozen time capsules still hold viable particles, and what could happen if they were to thaw naturally? The permafrost of Siberia acts as a deep freezer, sealing away organic material under permanently frozen layers, but that seal is weakening. As Arctic temperatures rise faster than anywhere else on Earth, permafrost is thawing in patches, exposing sediments that have not seen daylight for tens of thousands of years. In these thaw zones, scientists have documented bursts of microbial activity, ancient carbon releasing as methane and CO2, bacteria waking from dormancy, and in rare cases, ancient viruses reappearing. In 2016, researchers at Moscow State University reported reviving Pandora virus Yodoma, another ancient amoeba-infecting virus from a Siberian permafrost layer dated to about 48,500 years old. Like its predecessors, it posed no threat to animals or humans, but its survival across such an immense span of time proved that viral particles, if kept cold and stable, could remain infectious for geological durations. The implication is not limited to distant prehistory. Arctic permafrost often contains remains of extinct mammals such as mammoths, bison, and prehistoric horses. Their frozen tissues still hold viral and bacterial DNA. Some virologists believe that pathogens of Ice Age animals, possibly pox viruses or others similar to modern livestock diseases, could in theory re-emerge if permafrost melts rapidly. While the probability of human infection remains extremely low, the pathways of exposure are now a subject of serious research. In one incident in 2016, a heatwave in the Yamal Peninsula thawed reindeer carcasses buried since an anthrax outbreak in the 1940s. Spores of Bacillus anthracis revived, infecting new herds and killing a young boy. Although anthrax is bacterial, not viral, the event demonstrated that ancient pathogens can resurface under the right conditions. It was a real-world example of what the permafrost record had been warning about, that frozen soil is not inert and warming can unlock more than just greenhouse gases. Modern studies aim to identify which viruses could survive thawing and how stable their genetic material remains. Using metagenomic sequencing, researchers extract DNA directly from permafrost cores to catalogue what lies dormant. These analyses reveal extraordinary diversity. Viral families previously unknown, some distantly related to pox viruses, herpes viruses, and giant phages. Most are inactive fragments, broken down by radiation or time, but a few remain complete enough to function under the right laboratory conditions. To test safety, revived viruses are limited to amoebas as hosts, a biological containment strategy ensuring that they cannot infect humans or animals. Yet, the discovery's broader implications stretch beyond disease risk. Ancient viral sequences offer insights into the evolution of life itself, helping scientists trace how viruses have shaped ecosystems across epochs. The frozen Arctic acts as a genetic archive, preserving chapters of evolution erased elsewhere by time and decay. In some cores, viral DNA appears alongside that of Ice Age megafauna and ancient vegetation, revealing patterns of coexistence. Sequencing data show that viral populations once mirrored climate cycles, flourishing during warmer intervals and retreating as ice advanced. Each thaw and freeze buried a record of those ancient microbial communities, now accessible for the first time through modern genomics. The latest frontier is understanding how current warming might reactivate these frozen ecosystems. Satellite imagery shows expanding zones of permafrost collapse, thermokarst craters and thaw slumps exposing ancient layers. In the Yodoma region of eastern Siberia, where much of the world's Ice Age carbon is stored, the melt rate has accelerated. With it comes new organic input to rivers and lakes, feeding microbial life and potentially reviving long-dormant genetic material. The question scientists now face is less about whether ancient viruses exist, and more about what happens when they return to circulation. Most will pose no threat, their host long extinct, their structures too fragile for open environments. But the Arctic's thawing permafrost is revealing how deeply connected climate, geology, and biology have always been. Each layer opened is both a scientific discovery and a biological unknown, a reminder that the line between past and present in the frozen ground is thinner than it seems. Lake Elgygytgyn Impact Lake, Chukotka edge of northeast Siberia. In the far northeast of Siberia, not far from the Arctic Ocean, lies a lake that shouldn't exist where it does. Perfectly round, about 12 kilometers across, its dark waters sit inside an ancient crater surrounded by tundra and low mountains. This is Lake Elgygytgyn, a name that means White Lake in the local Chukchi language. It is one of the most remote and scientifically valuable places in the Arctic, a natural archive that has recorded the history of climate change for more than 3 million years. Elgygytgyn was not formed by glaciers or tectonic shifts, but by an impact. Around 3.6 million years ago, a meteorite slammed into the volcanic rocks of Chukotka, blasting out a crater more than 175 meters deep. Over time, it filled with water, forming a lake that has never dried out and, remarkably, was never covered by continental ice, even during the coldest glacial periods. That single fact makes it unique. Every layer of sediment at its bottom has remained undisturbed since the lake's birth. For scientists studying the Arctic's past, Elgygytgyn is a perfect time capsule. Each year, microscopic particles, dust, pollen, volcanic ash, and organic remains settled onto the lake floor, forming a layered record of the region's changing environment. These layers tell a continuous story of temperature swings, vegetation shifts, and atmospheric transformations reaching back millions of years. In 2009, an international drilling project finally reached the sediments buried beneath the lake. Working through 3.6 million years of deposits required drilling through more than 300 meters of frozen sediment and lake mud. Each meter represented thousands of years of history. The cores were flown to Germany and the United States for detailed analysis, revealing the most complete Arctic climate record ever recovered from land. What the cores showed surprised everyone. The Arctic, often imagined as a stable realm of ice and cold, turned out to have experienced enormous fluctuations, periods of warmth nearly unimaginable for the region today. In multiple intervals, the sediment contained pollen from trees like alder, larch and pine, species that now grow thousands of kilometers to the south. These green Arctic phases occurred during interglacial periods when temperatures were several degrees higher than today, and ice retreated far beyond the polar circle. During these warm episodes, Elgygytgyn's ecosystem changed completely. Sediments show bursts of biological activity. Diatoms, algae, and organic carbon concentrations increased sharply. Then, within a geological blink, cold conditions returned, locking the region back into permafrost and ice. These cycles repeated dozens of times over millions of years, offering a clear picture of how rapidly the Arctic can switch from warm to cold and back again. The core also recorded signals of super interglacials, unusually warm periods that stand out even among warm phases. One such interval, about 1.1 million years ago, appears to have been warmer than any modern interglacial, with sustained summer temperatures roughly 8 degrees Celsius higher than today. Tree pollen and magnetic data suggest open forests around the crater rim, lakes filled with meltwater, and near total loss of perennial snow. These findings challenged previous models that assumed the Arctic remained largely frozen throughout most of the Pleistocene. Even more striking are the transitions between these states. Chemical markers within the sediments, such as oxygen isotopes and magnetic mineral ratios, reveal how abrupt some shifts were. In certain layers, changes from warm to cold occurred in less than a few centuries, a reminder that Arctic climate systems can flip quickly once certain thresholds are crossed. The lake's sediments also preserve traces of volcanic eruptions, dust storms, and cosmic impacts. Layers rich in tephra record explosions from Kamchatka and the Kuril Islands. Iron-rich horizons point to shifts in magnetic polarity, which helps synchronize the record with global timescales. Through this combination of evidence, Elgygytgyn has become one of the reference points for reconstructing global climate change. Geologists compare its record to that of marine cores from the North Atlantic and Greenland ice cores to understand Arctic amplification, the tendency for temperature changes to be more extreme in polar regions. The sediments show that even small shifts in greenhouse gas levels or Earth's orbit produced outsized responses in the Arctic environment. During warmer intervals, the feedback from vegetation, albedo, and permafrost melting likely amplified global trends. The site also provides a natural laboratory for studying Arctic tipping points. In several intervals, the data show that once certain warmth thresholds were reached, the system entered a new self-sustaining state. Forests expanded, snow cover shrank, and local temperatures stayed high even as global averages cooled again. When cold returned, these processes reversed just as rapidly, freezing out vegetation and sealing carbon back into permafrost. The lake's history suggests that stability in the Arctic has always been temporary. Modern scientists return each summer, travelling hundreds of kilometres by helicopter, to collect water samples, sediment traps, and isotopic data. Beneath the ice in winter, they measure methane and oxygen levels, tracing the lake's ongoing chemistry. Even now, Yamal-Gydan reacts to modern warming. Its ice cover is thinner, and seasonal melt begins earlier each year. The lake that has withstood 3 million years of climate cycles is beginning to show subtle signs of change. For all its stability, questions remain about how such a lake persisted through so many glacial periods without being buried or drained. The crater's depth, regional topography, and low precipitation likely protected it. Permafrost surrounding the basin acts like a natural dam, trapping water even when ice sheets advance nearby. This unique geology allowed the lake to keep accumulating sediments without interruption, a perfect archive in one of the harshest environments on Earth. Today, the sediment cores from Lake Yamal-Gydan sit in laboratories in Europe, Japan, and Russia, each slice labelled and catalogued. Within their fine layers lie signals of past worlds, forests, ice sheets, fire, and wind, captured year by year across millions of years. As researchers continue to read this ancient diary, the Arctic's future and its fragile thresholds come into sharper focus, all written in the quiet depths of a crater lake that has never forgotten its impact. Born beginning, Popigai impact structure Taimyr Evenkia. In the northern expanse of Siberia, between the Taimyr Peninsula and the Evenkia region, the tundra hides the scars of an ancient cataclysm. It is a vast circle nearly 100 kilometers wide, eroded and filled with rock debris, snow and rivers. From above, it looks like the ghost of an explosion frozen in stone. This is the Popigai crater, one of the largest impact structures on Earth, the remnant of a collision that forever altered the local geology and left behind something remarkable: natural impact diamonds. The story begins about 35 million years ago, in the late Eocene. Earth was a different planet then, warmer, lush with forests that reached into the high latitudes. Somewhere in space, a stony asteroid about 8 kilometers across broke free from its orbit and entered the atmosphere at cosmic speed. In seconds, it struck the surface near what is now northern Siberia, releasing energy equivalent to billions of tons of TNT. The blast vaporized rock, leveled everything within hundreds of kilometers, and carved out a crater more than 100 kilometers in diameter and 5 kilometers deep. The impact melted and compressed the underlying crust, transforming the region's graphite-rich rocks into tiny diamonds through immense heat and pressure. Within microseconds, temperatures soared above 2,000 degrees Celsius, and pressures exceeded hundreds of thousands of atmospheres. Carbon structures inside the target rocks, mainly graphite layers, reconfigured into crystalline diamond lattice. The event was so powerful that the process mimicked industrial diamond formation, only on a planetary scale. Today, Popigai ranks among the 4 largest confirmed impact craters on Earth, alongside Chicxulub in Mexico, Sudbury in Canada, and Vredefort in South Africa. But unlike those sites, Popigai's remoteness kept it largely untouched for much of modern history. Its name comes from the Popigai River, which cuts across part of the structure. From ground level, the landscape reveals little of its violent past. Only concentric ridges, shattered rock outcrops, and circular valleys that betray the buried geometry of the crater. The first scientific recognition of Popigai's impact origin came in the 1970s. Soviet geologists analysing the region's unique rock textures discovered features impossible to explain by volcanic activity: shocked quartz, melt breccias and shatter cones, hallmark signs of a meteorite impact. Core samples confirmed widespread high-pressure minerals, including coesite and stishovite, which only form under extreme shock. These minerals proved beyond doubt that Popigai was not a caldera, but a giant impact basin. At the centre of the structure lies a melt sheet of glassy and crystalline rock, up to 1.5 kilometers thick, produced when the crust liquefied under the explosion. Surrounding it is a ring of fractured bedrock and uplifted strata that mark the rebound of the crust after impact, a geological splash frozen in time. In satellite imagery, this uplift forms a faint ring about 90 kilometers across. Beneath it, seismic surveys have mapped the crater's deep roots, revealing deformed basement rocks extending several kilometers down. But the most unusual product of the Popigai event is its impact diamonds. The target rocks of the region belong to ancient graphite-bearing metamorphic formations known as the Anabar Shield. When the meteorite hit, these graphite layers were instantaneously transformed. The result was a deposit of microscopic diamonds mixed with shocked rocks, breccias and melt. Many of these diamonds are only a few micrometers in size, though some aggregates reach millimeters across. Their structure is distinctive, irregular, often containing inclusions of other high-pressure minerals. Under microscopes they appear cloudy or grey rather than clear, reflecting their polycrystalline texture. These are not gem-quality stones, but they possess exceptional hardness, making them valuable for industrial applications such as abrasives and cutting tools. Soviet geologists estimated that the deposit could contain trillions of carats of these impact diamonds, dwarfing all known natural reserves combined. During the Cold War, Popigai became a site of strategic curiosity. Reports circulated in the 1970s and 1980s, suggesting that the Soviet Union considered developing the resource. Field teams from the Yakutsk and Krasnoyarsk geological institutes drilled exploratory cores and confirmed dense diamond zones within the crater's central uplift. But the site's remoteness, more than 1,000 kilometers from major infrastructure, and the small size of the crystals made large-scale mining uneconomical. Synthetic industrial diamonds, produced in laboratories at lower cost, eventually overshadowed Popigai's potential. Recent studies have refined our understanding of these diamonds. Electron microscopy and Raman spectroscopy show that many are Lonsdaleite, a hexagonal form of diamond believed to be even harder than the standard cubic structure. Lonsdaleite forms only during high-pressure shock conditions, the kind produced by a massive impact. Some samples from Popigai display a mixture of both forms, suggesting rapid transitions between crystalline states as shock waves pass through the rock. Geologists continue to debate the exact distribution of these diamond-rich zones. Some argue that the densest concentrations lie within the annular melt sheet near the central uplift. Others suggest they extend outward to the fractured graphite-bearing basement. Geophysical modelling also raises the possibility that multiple layers of diamond-bearing breccia occur at different depths, depending on local variations in carbon content and pressure gradients during impact. The Popigai impact also holds interest for planetary science. It provides a natural analogue for cratering processes on other worlds, how impacts reshape crusts, produce melt sheets, and synthesize high-pressure minerals. The crater's preservation under permafrost offers a pristine example of post-impact cooling and weathering over tens of millions of years. Although the diamond deposits remain untapped, they have become a focus of academic research rather than industrial ambition. Field expeditions led by the Russian Academy of Sciences still travel there in summer, collecting rock samples and mapping shock zones using drones and magnetometry. Each core drilled reveals new details about the temperature gradients, shock pressures, and chemistry of the impact plume. The data suggest that the Popigai event may have had global consequences. Its estimated energy release rivals that of the Chicxulub impact, which triggered the mass extinction 30 million years later. Sedimentary records elsewhere show coincident spikes in atmospheric dust and isotopic anomalies, hinting that Popigai's blast may have temporarily altered Earth's climate, though no mass extinction followed. Today the site remains desolate, a landscape of low hills, patterned ground, and frozen rivers. From orbit, its circular outline is faint but unmistakable, a reminder of an ancient collision between worlds. The diamonds locked within its rocks are silent witnesses to that instant of unimaginable force, when the Siberian sky turned to fire and stone became crystal in a single flash. Chinga iron meteorite, Tuva, in the mountains of southern Siberia near the border between Russia and Mongolia, lies a quiet valley where metal once fell from the sky. The local name for the place is Chinga, a river basin that cuts through the Tuva region. Scattered across its gravel and grasslands, explorers have found hundreds of metallic fragments, pieces of a meteorite that arrived long ago, so long that no trace of its impact crater remains. What survives instead is a mystery of metal, time, and disappearance. The Chinga meteorite was discovered by accident in 1913, when gold prospectors working along the Chinga River noticed heavy, metallic nodules glinting in the silt. At first, they thought they had found unusual ore, but the material's high nickel content and unique structure quickly revealed its extraterrestrial origin. Over the next decades, geologists and collectors recovered more than 250 kilograms of meteorite fragments across an area stretching over 20 kilometers. Yet no crater, no impact structure, and no clear fall pattern has ever been found. The metal itself tells a story that reaches back billions of years. The Chinga fragments are made of ataxite, a rare class of iron meteorite composed primarily of nickel-rich kamacite and teenite alloys. Unlike most iron meteorites, which show crystalline Widmanstatten patterns when etched, ataxites lack visible structure. Their metal cooled too quickly for large crystals to form. Chinga's composition includes about 16% nickel plus trace elements like gallium, germanium, and iridium, confirming its cosmic origin. Chemical analysis and isotopic dating show that the meteorite formed in the core of an ancient asteroid destroyed during the early history of the solar system. What remains are pieces of that metallic heart shaped by millions of years of collisions before finally being pulled into Earth's orbit. The fragments found in Tuva represent the last stage of that long journey, but how and when they arrived is still debated. Early studies propose that the meteorite struck the ground between 10,000 and 20,000 years ago, near the end of the last ice age. The evidence is circumstantial. The fragments lie mostly in glacial sediments and river terraces, suggesting that the fall predates modern topography. Radiocarbon dating of associated soils and oxidation crusts points to an age of roughly 15,000 years, though erosion and glacial reworking may have redistributed the pieces long after the initial impact. The absence of a crater remains the most puzzling feature. A meteorite of Chinga's size should have left a visible mark, yet none has been found despite multiple surveys. One explanation is that the meteor broke apart high in the atmosphere, producing a low-altitude airburst rather than a crater-forming impact. In that case, the fragments would have rained down over a wide ellipse, scattering across the surface as the blast dissipated. Another possibility is that the fall occurred on glacial ice that has since vanished, erasing any crater once present. When the ice melted, the fragments would have been carried downstream and redeposited in the river sediments where they were later found. Field mapping supports this second scenario. Many fragments were found embedded in layers of compacted gravel and sand, consistent with meltwater channels from glacial retreat. Some pieces show smoothed edges and oxidation patterns suggesting that they were transported by water after the fall. Others remain sharp, their fusion crusts intact, signs of minimal reworking. The mix of conditions hints at multiple episodes of movement, first the airburst, then glacial burial, then redeposition during post-glacial erosion. Microscopic study of the fragments reveals their violent history. Many pieces contain shear bands and recrystallized zones, formed when the meteorite was shocked during fragmentation. Small inclusions of troilite and schreibersite indicate rapid cooling after exposure to extreme heat, consistent with atmospheric breakup. These microstructures preserve a record of the moment when the meteor's internal stresses exceeded its strength, shattering it into hundreds of metallic shards. Magnetic measurements of the fragments show slight variations in orientation, implying that they cooled independently as separate pieces, not as part of a molten mass. This supports the view that the meteor disintegrated before impact rather than melting on the ground. The airburst would have released immense energy, perhaps comparable to a small nuclear explosion, but spread across a large area, leaving no single point of destruction. In Tuva's thin soils, oxidation has worked slowly. Some fragments still gleam when cleaned, others are coated with dark weathering crusts rich in iron oxides. A few have been found buried deep in peat bogs, where anaerobic conditions preserved them almost perfectly. Together, they offer a timeline of exposure that spans thousands of years, each layer recording a different stage of post-fall history. Recent isotope analyses refined the chemical fingerprint of Chinga, linking it to a rare group of nickel-rich ataxites similar to the Tibetan Nantan and Sikhote Alin falls. though those occurred much later in human history. The Chinga meteorite stands apart because it is ancient, older than recorded memory, its fall likely witnessed only by the wild animals that roamed the Pleistocene tundra. Some researchers have proposed that the fragments could represent secondary deposition from a larger parent body that fell elsewhere, but no source crater has been located within hundreds of kilometres. Aerial and satellite surveys reveal no circular depressions matching its composition. The lack of glassy impact melt or shock terrestrial rock strengthens the case for an atmospheric breakup. In 2017, advanced scanning electron microscopy revealed that some Chinga fragments contain nanometer-scale diamonds formed by high-pressure shock during fragmentation. These microdiamonds confirm that at least part of the body experienced pressures of several 100,000 atmospheres, a momentary transformation as it tore apart above the surface. Today, most of the recovered material rests in museums and research collections in Moscow, St. Petersburg and Ulan-Ude. The largest single mass weighs about 20 kilograms, but smaller pieces still appear occasionally when the Chinga River floods or cuts into new sediments. Locals have long known of the heavy stones, sometimes using them as tools or charms before their cosmic origin was understood. The mystery of Chinga lies not in its composition, but in its silence. Hundreds of fragments tell of an event powerful enough to scatter metal across kilometers of tundra, yet no trace of the fall itself, no crater, no eyewitness, remains. What endures are these iron relics shaped in the heart of an ancient world, broken in Earth's sky, and resting now in the quiet soil of Tuva, Yana RHS north of the Arctic Circle, on the banks of the Yana River in northeastern Siberia, more than 700 kilometers north of the Arctic Circle. Archaeologists uncovered something once thought impossible: a Paleolithic settlement older than the last ice age, frozen beneath layers of permafrost. The site is known as Yana RHS, short for Rhinoceros Horn Site, named after the remains of an Ice Age woolly rhinoceros found nearby. Its discovery changed the timeline of human presence in the Arctic, proving that people lived and thrived here 32,000 years ago, in conditions that would challenge even modern survival. The Yana site lies within a landscape of tundra and steppe, where winter temperatures still fall below -40 degrees Celsius and daylight disappears for weeks. Yet, tens of millennia ago, it was home to a group of hunter-gatherers who built shelters, crafted tools, and hunted some of the largest animals ever to walk the earth. Excavations revealed thousands of artifacts: stone blades, ivory needles, decorated objects, and bone weapons preserved in frozen soil along the river terrace. The permafrost sealed everything like a time capsule, even fragments of wood, antler, and charred bone. When the first dig began in 2001, led by Russian archaeologist Vladimir Petulko, few believed people could have reached such a latitude before the peak of the last glaciation. Most models suggested that northern Siberia was uninhabitable before 20,000 years ago, but radiocarbon dating of charcoal and bone from Yana showed ages between 27,000 and 32,000 years, pushing human occupation of the Arctic back by more than 10,000 years. The site's material culture reveals a people who mastered cold weather living in ways not yet fully understood. They hunted mammoth, bison, reindeer, and woolly rhinoceros, using finely crafted weapons made from mammoth ivory and stone. Cut marks on bones show skilled butchery, and piles of tusks suggest both hunting and scavenging. The sheer number of artifacts, more than 2,500 tools, implies a long-term or repeated settlement rather than a brief stopover. Among the most striking finds are ornaments carved from mammoth tusk, tiny pendants, beads, and stylized animal figurines. Some pieces were polished and drilled, evidence of symbolic behavior and artistic expression. Researchers also uncovered awls and needles made of bone, suggesting tailored clothing, a key adaptation to extreme cold. At these temperatures, exposure of even a few minutes could be fatal without insulated coverings, so the ability to sew fitted garments may have been essential for survival. Remains of small hearths and charcoal layers indicate that fire was used not only for warmth, but for light and tool making. Burnt ivory fragments show that mammoth bone served as fuel when wood was scarce. The evidence suggests that people lived here seasonally, perhaps during periods when herds migrated through the Yana Basin, following resources across the Ice Age landscape. The site also provided one of the earliest glimpses into the genetics of Arctic populations. In 2019, DNA extracted from 2 milk teeth found at Yana revealed a distinct lineage previously unknown to science. These children, boys who lived around 31,000 years ago, belonged to a group now called the Ancient North Siberians. Their genomes showed a blend of early West Eurasian ancestry with deep northern roots different from both later East Asian and European populations. This lineage once spread widely across Siberia, but eventually disappeared, replaced or absorbed by later migrations. Genetic studies link the ancient North Siberians to populations that later contributed to the ancestry of both indigenous Siberians and Native Americans. Their genetic signature persists faintly in the earliest peoples of Beringia, the now submerged land bridge that once connected Siberia to Alaska. This connection means the Yana population may represent one of the oldest branches of the human family that eventually peopled the Americas. How these people survived remains a puzzle. Average winter temperatures around 32,000 years ago hovered near 40 degrees C, with limited daylight and constant winds. The landscape offered no forests for shelter and little plant life for food. The Yana inhabitants relied on animal resources almost entirely. Meat for food, fat for heat, bones and tusks for tools, sinew for sewing, and hides for clothing and shelter. Their camp likely consisted of semi-subterranean dwellings, built from mammoth bones and covered with hides, similar to those found at later sites across northern Eurasia. The remains of foxes, wolves, and even small birds show that they used traps and specialised hunting strategies. Stone tools include scrapers, burins, and spear tips carefully crafted from local river pebbles. Some implements are so finely shaped that they rival later Upper Paleolithic technology from Europe. Microfaunal remains, tiny bones and pollen, help reconstruct the environment they lived in. At that time, the Yana Basin was part of the so-called Mammoth Steppe, a vast dry grassland stretching from Europe to Alaska. Grasses, sedges, and hardy shrubs covered the plains, supporting immense herds of grazing animals. This open habitat, while harsh, provided abundant prey for skilled hunters. The ancient North Siberians were also among the first known groups to exploit mammoth ivory on a large scale. Some tusks show precise shaping into rods and points, possibly components of composite weapons. Others were split to create blanks for carvings or ornaments. Ivory waste from production piles near hearths indicates an organised workspace, evidence of craft specialisation rare for such an early Arctic site. Sediment samples from the site show microscopic ash and charcoal spread over wide areas, hinting at controlled fire use. Hearths may have been surrounded by windbreaks made of bones and hides. These details, combined with the diversity of tools and the symbolic artefacts, reveal a social and technological sophistication unexpected for such an extreme setting. Even after 2 decades of research, many questions remain. How did these people navigate a frozen world where food and materials were scarce? Did they migrate seasonally, or stay through the dark winter months? How did they manage firewood in a treeless tundra? The Yana site holds pieces of the answers, but much of the story lies still buried in the permafrost. Each new excavation adds to the image of a culture that adapted beyond what was thought possible. A population living thousands of kilometres north of any other known human group of its time, building fires, crafting art, and hunting giants on a frozen plain at the edge of the world. Baikal sponge die-off since 2013. In the heart of Siberia lies a body of water so ancient and deep that it holds 1/5 of the planet's unfrozen fresh water. Lake Baikal, more than 25 million years old, is home to thousands of species found nowhere else on Earth. Its clear, cold water has long been a symbol of purity, a window into deep geological time. But in recent years, something strange has been happening beneath the surface. The rocks and reeds that once shimmered green and gold are turning pale, covered in dying sponges that crumble to the touch. The Baikal sponge, Lubomirskia baikalensis, is one of the lake's most recognisable inhabitants. It forms dense colonies along the rocky shallows, filtering the water and serving as habitat for countless microorganisms, crustaceans and larvae. For millions of years, these sponges have been silent guardians of the lake's clarity, processing nutrients and maintaining balance in an ecosystem so stable that scientists once called it the Galapagos of Russia. That balance began to shift around 2013, when divers and researchers started to notice large patches of sponges losing colour, collapsing and disappearing. At first, the phenomenon seemed localized, a few infected sites near popular coastal towns. But within 2 years, the disease had spread across the western and southern shores, killing sponges over vast areas. Their once vibrant green hue, given by symbiotic algae living inside their tissues, faded to white and grey. The skeletons broke apart, and soon the lakebed was littered with their remains. By 2017, reports described die-offs reaching several metres deep, a sight never before seen in the lake's long history. Scientists rushed to find the cause. Samples taken from affected areas revealed that the sponges were suffering from mass bleaching, similar in appearance to the coral bleaching seen in tropical reefs. The algae inside their tissues, tiny photosynthetic symbionts, were dying or being expelled, leaving the sponges weak and vulnerable to infection. But what triggered the loss of these algae, and why now, in one of the coldest, cleanest lakes on Earth? Researchers soon found multiple stressors converging at once. Pollution from nearby settlements had increased significantly, especially near the cities of Listvianka and Severodbaikalsk. Runoff from tourism, untreated sewage, and detergents introduced nutrients such as nitrogen and phosphorus into the water, promoting algal blooms and bacterial overgrowth. These changes altered oxygen levels and water chemistry, affecting the delicate symbiosis within the sponges. At the same time, the water temperature in Baikal has been rising, a trend measured for decades. The lake is warming faster than the global average, about 1 degree Celsius over the last half-century, which may not sound like much but has a profound effect on cold-adapted organisms. Warmer water holds less oxygen and accelerates microbial activity, creating favourable conditions for pathogens. Genetic studies have identified bacterial communities in disease sponges dominated by Pseudomonas, Acinetobacter and Aeromonas, bacteria known for infecting aquatic animals under stress. Adding to the complexity are invasive species introduced by human activity. One of them, the Detomurosylenia sibirica, forms thick biofilms that cover rocks and smother native algae. Another, the filamentous alga Spirogyra, has expanded explosively since 2011, forming dense green mats near shores where waste and warm runoff enter the lake. These blooms clog the substrate and compete with sponges for space and light, altering the flow of nutrients that once sustained them. In 2020, Russian and Japanese scientists working with the Limnological Institute in Irkutsk performed detailed molecular analyses of diseased sponge tissue. They found strong signatures of bacterial infection and oxidative stress, cells producing reactive oxygen molecules, a hallmark of environmental toxicity. Yet no single pathogen explained all the symptoms. Instead, the evidence pointed to a multifactorial crisis, where rising temperatures, pollution, and microbial shifts interacted in ways that amplified damage. The sponge's symbiotic algae, once thought to be resilient, appear highly sensitive to temperature and nutrient changes. When they die or leave the sponge tissue, the host loses its main energy source and becomes defenseless. The once spongy body collapses, and opportunistic bacteria move in, accelerating decay. In some regions, this process has become nearly continuous during summer months, preventing a recovery between years. Divers have documented entire underwater landscapes transformed. Where once there were thick carpets of green sponges, now there are bare stones covered in slime and decomposing biofilms. The loss extends beyond aesthetics. The filtering capacity of Baikal sponges is immense, each colony cycling thousands of litres of water per day. Their collapse affects water transparency, oxygen levels, and the entire food web, from microscopic plankton to fish species that depend on clear, oxygen-rich habitats. Some researchers have compared the event to a slow-motion ecological tipping point. Baikal's stability has always depended on its cold, oxygenated water and isolation from human pressures. But as climate change warms the region and development expands along the coast, the lake's unique balance is being tested. The sponge die-off is both a symptom and a signal, a visible manifestation of invisible chemical and biological shifts occurring across the ecosystem. Efforts to understand the crisis continue. Teams from Russia, Japan, and Germany monitor affected zones using underwater drones and remote sensors. They analyze DNA from microbes, temperature data, and nutrient flows, trying to reconstruct the chain of events leading to disease. Experiments in controlled aquaria have shown that small increases in temperature, combined with organic pollution, can reproduce bleaching symptoms within weeks. These findings reinforce the idea that the sponge's symbiosis is finely tuned to Baikal's historical conditions and breaks down quickly under modern stress. One surprising discovery came from deep water samples taken far from human influence. Even there, scientists found signs of sponge stress and microbial imbalance, suggesting that the drivers are not purely local. Climate-driven warming and long-range atmospheric pollutants, including industrial compounds and microplastics, may also play a role. Analyses of sponge tissue have detected traces of heavy metals and hydrocarbons, substances transported from distant factories by air and river systems. Despite the scale of the problem, some areas of the lake still harbour healthy sponge populations. In the colder northern basin, where water remains clearer and nutrient levels lower, colonies continue to grow and reproduce. These regions may serve as natural refuges, allowing the species to persist even as southern habitats degrade. The story unfolding in Baikal is one of contrast, between the lake's age and the speed of modern change, between resilience and fragility. What scientists see now is not a single cause, but a network of pressures reshaping an ecosystem that has survived ice ages, tectonic shifts, and millennia of isolation. The sponges that once filtered its depths are revealing how even the oldest and purest waters can be pushed to their limit when the world around them begins to warm. Siberian Traps and the Great Dying Permian Triassic. In the remote reaches of northern Siberia lies one of the most haunting scars in Earth's deep past, a vast landscape of ancient lava fields known as the Siberian Traps. To the untrained eye, it's just endless basalt plateaus and rugged cliffs stretching toward the Arctic horizon. But to geologists, this region marks the site of one of the most catastrophic events in the history of life, the Permian Triassic extinction, often called the Great Dying. 252 million years ago, this place became the centre of a planetary crisis so severe that it nearly erased life itself. The story begins at the end of the Permian period, when Earth was a single supercontinent known as Pangaea. It was a time before dinosaurs, when strange reptiles, primitive mammals, and giant insects dominated the land. Then, in what seems like an instant in geological terms, the world changed. Vast fissures opened across Siberia, unleashing floods of molten rock that covered more than 7 million square kilometres, an area larger than Europe. The eruptions lasted for nearly 1 million years, layering the landscape with up to 5 kilometres of basalt. These eruptions weren't ordinary volcanic events. They were continental flood basalts, massive outpourings of magma from deep within the mantle. Each pulse released not only lava but vast quantities of gas, carbon dioxide, sulfur dioxide and methane, into the atmosphere. As the lava burned through thick deposits of coal, limestone and evaporate rocks, it produced even more greenhouse gases and toxic compounds. The air would have been thick with soot and aerosols, turning sunlight into a dull red glow. At first, the damage might have seemed local, acid rain, darkness and collapsing ecosystems across Siberia, but over time the effects spread globally. The volcanic gases triggered a runaway chain reaction in the climate system. Carbon dioxide drove rapid global warming, while sulfur aerosols caused short-term cooling and acid rain. The temperature fluctuations disrupted ocean circulation, leading to oxygen depletion and the buildup of hydrogen sulfide in the seas. The result was catastrophic. Within a few 100,000 years, more than 90% of marine species and 70% of terrestrial species vanished. Coral reefs collapsed, forests disappeared, and even insects, one of the most resilient groups in evolutionary history, suffered massive losses. The fossil record shows layers of black shale and ash marking this interval, evidence of an Earth that became hostile to life itself. The link between the Siberian Traps and the Great Dying is now widely accepted, but the exact kill mechanism remains one of the great scientific debates. Some researchers point to the sheer volume of CO2 released, which could have raised global temperatures by 5 to 10 degrees Celsius and turned oceans acidic. Others highlight the release of methane from destabilised permafrost and seafloor clathrates, amplifying the greenhouse effect. Another hypothesis focuses on halocarbons, chlorine and bromine compounds produced when magma interacted with salt-rich rocks. These gases could have destroyed the ozone layer, exposing Earth's surface to lethal ultraviolet radiation. There's also evidence that volcanic nickel emissions nourished blooms of methane-producing microbes, further driving warming and ocean anoxia. Recent studies using uranium-lead dating on zircon crystals have refined the timeline of the eruptions. The most intense phase appears to have lasted less than 60,000 years, an eye blink in geologic time but long enough to destabilize every major ecosystem. Sediment cores from South China, the Arctic, and the Middle East show synchronized spikes in mercury, a chemical fingerprint of volcanic emissions, confirming the global reach of Siberia's eruptions. In Siberia itself, remnants of these eruptions remain visible across thousands of kilometers. Cliffs near the Tunguska and Norilsk regions reveal stacked lava flows, each representing a separate pulse of activity. Between them are layers of baked sediment, evidence of brief pauses when vegetation tried to recover before being smothered again. Geologists estimate that over the course of the event, millions of cubic kilometers of magma erupted, releasing as much as 100 trillion tons of carbon into the atmosphere. What makes the Siberian Traps so deadly is not just their size, but their setting. Beneath the region lay thick deposits of coal-bearing sediments, salt domes and carbonates. As magma intruded into these layers, it cooked them, releasing additional greenhouse gases and halogen compounds. Geochemical models suggest that this contact metamorphism may have been the tipping point that transformed a regional eruption into a planetary disaster. The environmental fallout can be traced in rocks far from Siberia. In ancient marine sediments, fossils of plankton vanish abruptly, replaced by evidence of bacterial mats that thrived in oxygen-starved waters. Carbon isotope data show a sharp negative shift, indicating a massive injection of light carbon from volcanic or biological sources, possibly methane. The oceans became warm, stratified and toxic, while land ecosystems faced drought and acid rain. Forest soils turned barren, rivers ran black with ash, and entire food webs collapsed. It took Earth millions of years to recover. For a long stretch after the extinction, the planet was almost silent. Coral reefs vanished entirely. The few surviving species lived in simplified, low-diversity ecosystems dominated by opportunistic organisms that could tolerate extreme heat and low oxygen. In the aftermath, new evolutionary experiments began to take shape, ancestors of dinosaurs, mammals, and modern marine life, rising from the ashes of catastrophe. Yet even now, scientists continue to uncover new clues buried in Siberia's frozen ground. In some areas near Norilsk and Puturana, ancient lava flows still contain gas vesicles and mineral inclusions that record the chemistry of the atmosphere at the time of eruption. Isotopic analyses of these inclusions reveal variations in carbon and sulfur consistent with repeated pulses of volcanic degassing. Others study the microscopic structure of sediment layers that bracket the extinction horizon, searching for the sequence of events that turned volcanic heat into global collapse. One of the most intriguing discoveries involves nickel-rich aerosols found in the rock record. The Siberian Traps are unusually rich in nickel ore deposits, now mined extensively near Norilsk. During eruption, fine nickel particles may have entered the atmosphere and oceans, acting as nutrients for certain microbes. These microbes, known as methanogens, produce methane, a greenhouse gas far more potent than CO2. A surge in their activity could have accelerated warming, linking the deep Earth's chemistry directly to the biosphere's collapse. Across the modern Siberian plateau, the evidence of this ancient disaster lies hidden under tundra and forest. Black basalt cliffs, frozen river gorges, and mountain ridges that once glowed red with molten rock. To stand there today is to see both the endurance of the planet and the fragility of its balance. The Siberian Traps remain a monument to the moment when the Earth's interior and atmosphere collided in a way that almost ended life, leaving behind a record still being read from the rocks of a land that remembers everything. Cave lion and mammoth permafrost mummies, Yakutia, Taimyr. In the frozen north of Siberia, where temperatures drop below -50 degrees and the landscape stays locked in ice for most of the year, the past refuses to disappear. Each summer, as permafrost thaws along riverbanks and hillsides, the ground releases bodies, not fossils, but entire animals from the Ice Age, preserved so well that fur still shines, skin still folds, and sometimes even the smell of flesh remains. These are the permafrost mummies of Yakutia and the Taimyr Peninsula. mammoths, woolly rhinos, bison, horses, and even cave lions, trapped in time for tens of thousands of years. One of the first of these astonishing discoveries was the Berezovka mammoth, unearthed in 1901 near the Kolyma River. Its body was nearly complete, with skin, hair, and internal organs intact. When scientists thawed it in St. Petersburg, they found semi-digested plants still in its stomach and signs of suffocation, as if the animal had fallen suddenly into frozen mud and died almost instantly. Since then, dozens of similar finds have surfaced across Siberia, revealing a record of life and death frozen beneath the tundra. In 2010, reindeer herders in the Yukagir region of Yakutia stumbled upon another extraordinary find: the severed head of a steppe wolf, nearly 40,000 years old. Its brain, teeth, and fur were still preserved, the ice having sealed it like a biological capsule. Nearby, scientists recovered the remains of several cave lions, extinct predators that once ruled the steppe. Two of them, cubs only a few weeks old, were found in 2015 near the Semyueliak River. They were so well preserved that their whiskers, paw pads, and golden fur remained untouched by time. These cubs, nicknamed Uyan and Dina, dated to roughly 14,000 years ago. Later discoveries brought even more detail. A third cub, called Sparta, found in 2018 was almost perfectly intact, complete with claws, fur, and inner organs. Scans revealed bones fully articulated and muscle tissue soft enough for histological analysis. It was the best preserved Ice Age cat ever found. Researchers studying the cub's stomach contents and tissues discovered traces of mother's milk and environmental pollen, clues to their short lives and sudden deaths. What makes these finds so striking is not just their state of preservation, but what they suggest about the conditions inside permafrost. In most parts of the world, even bones decay in a few thousand years, but in Siberia's permafrost, constant cold, dryness, and lack of oxygen can halt decomposition almost entirely. When an animal dies and is quickly buried in silt, the freezing process locks in water molecules before bacteria can begin to break them down. In this deep freeze, tissue, DNA, and even proteins remain intact for tens of millennia. Yet not all mummies are equal. Some bodies are desiccated and partial. Others, like the Yucca mammoth, found in 2010 near the Laptov Sea coast, seem almost lifelike. Yucca was a young female, about 6 to 8 years old, dated to roughly 39,000 years ago. Her fur still covered her body, and her trunk, ears, and tail were intact. When scientists examined the carcass, they noticed strange signs: circular wounds on her back and skull fractures that suggested scavenging or even possible interaction with humans. Though the latter remains debated, the find provided rare access to soft tissues, brain matter, and muscle fibres in remarkable condition. In 2013, another mammoth, named Buttercup, emerged from the Mali-Liakovsky Island permafrost. When researchers began thawing the carcass, they noticed something astonishing: dark, viscous liquid oozing from the body cavity. Early media reports described it as liquid blood, preserved for 40,000 years. The team, led by the Northeastern Federal University in Yakutsk, collected samples under sub-zero temperatures, hoping to analyse the material before it degraded. Later studies showed that while the red fluid was not true blood, it did contain hemoglobin remnants and tissue plasma, providing rare biochemical evidence of cellular preservation at near-Arctic conditions. The presence of such fluids raised questions about microenvironments within frozen carcasses. How could organic molecules, fragile under normal conditions, persist for so long? Analysis suggests that salts and cryoprotective compounds, natural antifreezes produced by body fluids or bacteria, may help stabilize tissues at sub-zero temperatures. In sealed ice cavities, these chemicals create isolated pockets where decay halts but structural integrity remains. Another puzzle lies in the colour and composition of preserved tissues. Some mammoth flesh appears bright red, others deep brown or blue-grey. These hues result from the chemical reactions of iron and oxygen over millennia, but in some cases, the pigment molecules are so intact that they still react to tests for blood proteins. Even the smell, described by researchers as a mix of wet wool and organic decay, reminds scientists that these are not fossils turned to stone but real biological remains frozen between life and geology. Beyond mammoths and lions, permafrost has yielded entire ecosystems frozen mid-scene. Bison with stomachs full of tundra grass, foals preserved with eyelashes and soft skin, and rhinos whose horns and hide still bear scratches from Ice Age predators. Each specimen offers a direct link to the steppe ecosystem that once stretched from Europe to Alaska, an environment of cold grasslands teeming with life now long gone. The preservation also opens a window into ancient genetics. Using DNA extracted from these frozen remains, scientists have reconstructed complete genomes of woolly mammoths and cave lions, revealing how they adapted to the cold. Mutations for thick fur, fat metabolism, and temperature-sensitive hemoglobin. These same sequences are now used in laboratories studying de-extinction, an effort to understand whether genes from these Ice Age species could one day be revived or reintroduced into living relatives like elephants. But the forensic details of preservation remain one of the great enigmas. Why do some carcasses emerge almost pristine, while others only a few meters away are degraded beyond recognition? Researchers suspect it depends on microclimatic factors. Whether the animal was buried during summer thaw or winter freeze, the grain size of the sediment, and how groundwater moved around it. Small variations in soil chemistry can mean the difference between a skeleton and a lifelike mummy. In Yakutia, local reindeer herders are often the first to spot these remains, exposed by river erosion or landslides triggered by thawing permafrost. The discoveries are increasing as the Arctic warms. Each summer, as the active layer of permafrost deepens, more ancient carcasses come to light. Some are quickly collected by scientists, others lost to scavengers or decay once exposed to the air. The work of preserving what the permafrost releases is delicate and urgent. Once thawed, tissues begin to decompose within hours, forcing teams to extract samples and refreeze them before they vanish. Inside laboratories in Yakutsk and St. Petersburg, researchers cut thin slices of frozen tissue to study under microscopes, tracing capillaries still filled with remnants of blood, muscles that retain elasticity, and hair follicles that show seasonal growth rings. Each specimen tells the story of a life that ended suddenly, trapped in mud, buried by snow, or frozen during a storm, and then suspended in time. The permafrost became not just a grave, but a vault, holding biological information that no fossil could preserve. Hair, organs, even traces of blood and smell. The smallest details of Ice Age life, sealed beneath Siberia's eternal ice, waiting to reappear as the ground begins to thaw again. Baikal Rift, magnetic tectonic anomalies. At the heart of Siberia, surrounded by mountains and forests, lies a crack in the earth that is still widening. Beneath the calm, mirror-like surface of Lake Baikal, the planet is pulling itself apart. The Baikal Rift Zone is one of the few places on Earth where a continent is actively splitting from within, a process that, over millions of years, could form a new ocean. But what makes this region even more intriguing are the invisible patterns beneath the water, magnetic anomalies and seismic signatures that defy simple explanation. They tell a story of hidden forces, heat, metal, and motion, shaping one of the deepest rift valleys in the world. Baikal may look like a tranquil freshwater lake, but it is also the world's deepest and oldest continental rift, reaching depths over 1,600 meters and stretching more than 600 kilometers from north to south. Satellite imagery reveals a long, slender scar cutting through the Siberian crust, bordered by steep faults and active mountain fronts. It's a place where the crust is thinning, the mantle is rising, and the landscape is literally being torn apart. When scientists began to map the rift in the 1960s and 1970s, they noticed something unusual. Measurements of Earth's magnetic field across the lake showed sharp fluctuations, zones where the field strength suddenly increased or decreased over short distances. These magnetic anomalies could not be explained by surface rocks alone. They hinted at large, magnetized bodies buried deep beneath the rift floor, arranged in patterns unlike those seen in other continental settings. Modern surveys using airborne and satellite magnetometry have refined those early findings. The central Baikal Basin, the deepest part of the rift, exhibits alternating magnetic highs and lows, sometimes aligned with known faults, sometimes cutting across them. In certain areas, magnetic signatures are so strong that they distort compass readings, while in others, the field drops to unexpected lows. These patterns coincide with seismic anomalies, regions where earthquake waves slow down or speed up as they travel through the crust. To understand what causes these signals, scientists combined magnetic, gravity and seismic data. The results show that the Baikal Rift is not just a crack in the crust, but a dynamic, multi-layered system. Beneath the lake lies a thick sequence of sediments, up to 9 kilometers deep, resting on a basement of highly magnetized igneous rocks. Below that, a hot, partially molten mantle plume may be rising, weakening the crust and driving extension. The presence of molten or heated material could explain why seismic waves slow down in some regions, while magnetized rocks create irregularities in the magnetic field. But the data don't line up perfectly. In some areas, strong magnetic highs occur where seismic velocities are low, suggesting localized magma intrusions or iron-rich rock bodies. In others, magnetic lows coincide with cooler, fractured zones. These mismatches complicate the picture, hinting at different processes operating simultaneously: tectonic stretching, magmatism, fluid circulation, and metamorphism, all interacting beneath the rift floor. One of the most striking anomalies lies in the central Baikal basin, near Wrangel Island. Here, magnetic intensity changes by more than 500 nanoteslas over just a few kilometers, an enormous shift for a continental setting. Geological mapping suggests that the anomaly corresponds to a buried intrusion of mafic rock, possibly related to ancient volcanic activity when the rift first began forming about 25 to 30 million years ago. These intrusions may still influence the lake's geothermal structure today. Deep seismic imaging adds another layer of complexity. In some profiles, the crust beneath Baikal appears unusually thin, just 30 to 35 kilometers, compared to the typical 45 kilometers in surrounding regions. The mantle below shows patches of low-velocity zones, interpreted as hot, possibly partially molten material. This thermal anomaly could explain both the magnetic irregularities and the region's frequent shallow earthquakes. The Baikal Rift is seismically active even now. Tremors occur every few months, some strong enough to rattle nearby towns like Irkutsk or Severobaikalsk. Most earthquakes cluster along the lake's western margin, following major faults such as the Primorsky and Morskoy zones. Yet, curiously, the distribution of seismicity doesn't always match the expected fault geometry. Some events occur within the basin itself, where the crust should be stretching quietly rather than fracturing violently. The mismatch between observed earthquakes and mapped faults remains one of the unresolved puzzles of Baikal's geodynamics. Temperature gradients measured in boreholes along the rift also reveal anomalies. Some parts of the lake floor emit higher than expected heat flow, suggesting active hydrothermal circulation. These warm zones often coincide with magnetic highs, supporting the idea that heated fluids move through magnetite-rich rocks. Hydrothermal vents have been observed in Baikal's depths, releasing methane, carbon dioxide, and mineral-rich water, signs that the rift remains alive, its geological pulse still beating. Another source of complexity comes from gravity measurements, which show subtle density contrasts in the crust. The data indicate that dense mafic intrusions, possibly remnants of ancient magma chambers, are embedded within lighter continental rocks. As these dense bodies cool and contract, they may influence stress distribution, triggering small earthquakes or affecting local magnetism. In short, the Baikal Rift is a geological patchwork, a mixture of hot mantle upwelling, cold continental blocks, ancient intrusions, and modern sediment fill. Some researchers propose that the rift's magnetic anomalies reflect the transition from brittle to ductile deformation, where the crust changes from cracking to flowing with depth. This transition could create complex magnetic fabrics, as minerals realign or remagnetize under strain. Others point to fluid-driven alteration, where circulating groundwater changes the magnetic properties of rocks over time. The result is a shifting pattern of magnetism that evolves as the rift continues to open. Despite decades of study, the exact driving mechanism of the Baikal Rift remains debated. Some geophysicists argue it's a result of far-field tectonic forces linked to the ongoing collision between India and Eurasia that pushes Siberia eastward. Others believe a mantle plume beneath Central Asia provides the heat and uplift needed to thin the crust. The truth may involve both, a combination of deep thermal anomalies and surface stresses working together to tear the continent apart. New geophysical models built from satellite and magnetotelluric data are revealing ever finer details. Beneath the rift, researchers have identified zones of high electrical conductivity, likely representing fluid-rich pathways or pockets of partial melt. These pathways align with both magnetic highs and seismic clusters, suggesting that fluids and heat migrate through the crust in interconnected channels. Even today, Lake Baikal's calm surface hides an active engine below. The same forces that formed its deep basin continue to reshape it, creating magnetic ripples, thermal gradients, and earthquake swarms that mark the restless boundary between past and future geology. Each survey adds another piece to a puzzle still unfolding, a rift caught in motion, magnetic and alive beneath the ice-cold waters of Siberia. Across thousands of kilometers, Siberia remains a living archive of Earth's extremes. From buried craters to frozen mummies, from shifting rifts to melting ice, its mysteries connect the deep past with the world we live in now. The land keeps revealing new signs, quiet reminders that even the oldest places on the planet are never truly still.